GCE Advanced Level Chemistry Practical Series Experiment number 34. Experimental study of the effect of temperature on the system of nitrogen dioxide and dinitrogen tetroxide gas. Aims is to develop a better understanding of dynamic chemical equilibrium in a gaseous system. So, one of the aims of this experiment is to develop a better understanding of dynamic chemical equilibrium. Dynamic chemical equilibrium in a gaseous system. And to investigate the effect of application of some stress on the equilibrium position of an equilibrium system. So, we are going to notice when we apply some stress on the equilibrium system, how the equilibrium position would change. Introduction. Changes in concentration, temperature or pressure can stress an equilibrium system and may cause a shift in the position of the equilibrium. The Le-Chatelier's principle provides insight into how altering aforementioned conditions can influence the equilibrium. So students, as I mentioned earlier, an equilibrium system can be stressed when we change these factors: concentration, temperature and pressure. So when we change these factors, the equilibrium position of the equilibrium may shift either towards the forward direction or the reverse reaction direction. So Le-Chatelier's principle gives us an idea when a system is stressed, in which direction the equilibrium position is going to shift to. So Le-Chatelier's principle gives us an idea when a system is stressed to which direction the equilibrium position is going to shift. Right students, so let's move on to the next slide. So here we have a brief overview of Le-Chatelier's principle. Le-Chatelier's principle states that if a system in equilibrium is subjected to a change in temperature, pressure or concentration of reactants or products, the system will adjust to counteract the change and restore a new equilibrium. Or in other words, when we change the temperature, pressure or concentration of reactants or products in an equilibrium system, the current equilibrium will be disturbed. However, the system will try to counteract the change we have made. System will try to somehow, to a certain extent, reverse the change that we have introduced into the system. Example, when the temperature is increased in equilibrium system. When the temperature of a system is increased, it will favor the endothermic reaction, leading to a temporary increase in the rate of the endothermic reaction. Endothermic reaction rate will temporarily increase. Endothermic reaction rate will temporarily increase when we increase the temperature of a equilibrium system. So students, when we increase the temperature of an equilibrium system, the system would try to bring down the temperature. So that is what Le-Chatelier's principle states. The system will try to oppose the change that we bring about. So when we increase the temperature of the system will try to bring the temperature down. Now, in equilibrium system, there will be a forward reaction as well as a reverse reaction. If the forward reaction is exothermic, the reverse reaction is going to be endothermic. If the forward reaction is endothermic, then the reverse reaction is going to be exothermic. So students, endothermic means energy absorbing reactions, exothermic means energy releasing reactions. So when we increase the temperature of a system, the system will try to favor the endothermic reaction, energy absorbing reaction. So the energy that we provide, the system will try to absorb that energy and favor the endothermic reaction. So momentarily the rate of the endothermic reaction will increase. Momentarily the rate of the endothermic reaction will increase, and little by little the exothermic rate will also increase, and at one point both the reaction rates will be equal to one another, and at that point a new equilibrium will be obtained. So students, when we are discussing these kind of theory paths, you have to very clearly understand there's not going to be only an increase of the endothermic reaction. Whenever we increase the temperature of any reaction, due to the increase of the temperature, the average energy of the entire system will increase. So therefore, both the forward reaction rate as well as the reverse reaction rate or backward reaction rate will also increase. Right? Both the reaction rates will increase. However, momentarily, there's a greater rate observed in the endothermic reaction, because when we increase the temperature, the system will try to bring down the temperature by doing the energy absorbing reaction more. So endothermic reaction will be favored. We use the word favored to indicate that momentarily the reaction rate of the endothermic reaction will increase, but after a while even the exothermic reaction rate will slightly increase. At one point both the reaction rates will be equivalent to one another. That means the forward reaction rate will be equivalent to the reverse reaction rate when the new equilibrium is obtained. So students, keep in mind, initially when we increase the temperature of a system, we say the endothermic reaction or energy absorbing reaction will be favored. So the rate of the endothermic reaction will surpass the rate of the exothermic reaction for a short period of time until the new equilibrium is obtained. If the endothermic reaction is the forward reaction, its rate will momentarily increase compared to the rate of the exothermic reaction, prompting the equilibrium position to shift to the right. So if you talk about a equilibrium where the forward reaction is the endothermic reaction, then the forward reaction rate will increase momentarily, and when a new equilibrium is formed, the equilibrium position is now shifted more towards the forward direction, or we say equilibrium position has shifted more towards the right hand side. Example, when the temperature is decreased in equilibrium system. When the temperature of a system is lowered, the reaction that produces heat will be favored. This means the exothermic reaction will be favored. As the temperature is decreased, an overall decrease in both the forward and the reverse reaction can be observed. However, due to the favoring of the exothermic reaction, the rate of the exothermic reaction will momentarily be higher than the rate of the endothermic reaction. If the reverse reaction happens to be the exothermic reaction, the reverse reaction will temporarily have a higher rate compared to the forward reaction, causing the equilibrium position to shift to the left. So students, as I mentioned earlier, when we increase the temperature of a system, both the forward and the reverse reaction rates will increase. When you increase the temperature of a system or any reaction, the reaction rate will increase. Right? So at that point, apart from increasing both the forward and the reverse reaction rate, the endothermic reaction was favored. So endothermic reaction rate was greater than the exothermic reaction rate in the initial parts of developing an equilibrium. At the point at which the equilibrium is developed, the forward and the reverse reaction rates are the same. But until the equilibrium is developed, the endothermic reaction rate was greater than the exothermic reaction rate. Until they obtain the equilibrium, there's going to be a slightly higher rate for the endothermic reaction than the exothermic reaction when we increase the temperature of a system. So when we lower the temperature of a system, the opposite of this happens. When we lower the temperature of a system, as mentioned here, when we lower the temperature of a system, both the forward and the reverse reaction rates will go down. However, according to Le-Chatelier's principle, when we lower the temperature of a system will try to increase the temperature. So that means system will try to carry out the exothermic reaction more. So the exothermic reaction will be favored. As you know, in a reversible reaction, there will be two reactions, forward reaction and the reverse reaction. If the forward reaction is exothermic, the reverse reaction is endothermic. If the forward reaction is endothermic, reverse reaction is exothermic. So if we consider the reverse reaction to be the exothermic reaction here, when we lower the temperature, although both the forward and the reverse reaction rates will come down, the exothermic reaction rate, which is the reverse reaction rate, is going to be slightly higher than the endothermic reaction rate or the forward reaction rate. So that means as soon as this equilibrium is disturbed, initially what you are going to observe is a slightly higher reverse reaction rate compared to the forward reaction rate. So therefore, equilibrium position shifts to the left in the reverse direction or in the backward direction. It shifts to the left. So students, when this is happening, we say, after the second equilibrium is obtained, we say equilibrium position has shifted more towards the reactant side or more towards the left. So here students, we have a equilibrium given. We have one complex ion turning into another in the presence of chloride ions, and this is a reversible reaction. And you can see the enthalpy value for this equilibrium is given as delta H greater than 0, meaning enthalpy change is a positive enthalpy change. So usually when you write the enthalpy change like this enthalpy change means the forward reaction is going to have a positive enthalpy value. So the enthalpy values that you usually get towards the right hand side like this communicates to us the enthalpy change of the forward reaction. So the forward reaction is a positive enthalpy value. That means the forward reaction is endothermic. So that means the reverse reaction is going to be exothermic. When the temperature of a system is decreased, the reaction that generates heat, namely the exothermic reaction, is favored. Lowering the temperature of a reaction leads to an overall decrease in both the rates of the forward and the reverse reactions. However, due to the preference for the exothermic reaction, its rate momentarily will be greater than that of the endothermic reaction. So we know if you are given an equilibrium like this, if you increase the temperature, we know the endothermic reaction will be favored momentarily. Momentarily means until the new equilibrium is obtained, one rate will be higher than the other. At the point at which you obtain the new equilibrium, both the rates are going to be equal once again. But until the new equilibrium is obtained, one rate will be greater than the other. So when we increase the temperature of a system like this, since the forward reaction is endothermic, the forward reaction rate will be greater, producing more and more of these products. And the reverse reaction rate will be smaller until the new equilibrium is obtained. So at the point at which the new equilibrium is obtained, we can see compared to the previous equilibrium, the product concentrations would have gone up and the reactant concentrations would have gone down. So we say equilibrium position has shifted more towards the right hand side. If the temperature is lowered, then the exothermic reaction will be favored, meaning the reverse reaction in this case. So exothermic reaction will be favored. So as soon as we lower the temperature, the rates of both the reactions will come down. However, the reverse reaction rate will be a higher rate compared to the forward reaction rate. So therefore, the products here will start to convert more into reactants faster than the reactants convert into products. So therefore, there will be a slightly higher reactant concentration compared to the first equilibrium, and the product concentration will be lower compared to our initial equilibrium. So we say equilibrium position will shift to the left when we lower the temperature due to the exothermic reaction, in this case the reverse reaction, being favored. If the reverse reaction is the endothermic one, it will temporarily exhibit a higher rate than the forward reaction, prompting the equilibrium to shift to the right. So not in relation to this equation, but however, in this particular statement states, if the reverse reaction is the endothermic one, it will temporarily exhibit a higher rate than the forward reaction, prompting the equilibrium to shift to the left. So when we increase the temperature, if the reverse reaction is the endothermic one, it will shift the equilibrium position accordingly. According to the above examples, it's clear when the temperature of a system is increased, the heat absorbing reaction, namely the endothermic reaction, will be favored. When the temperature of a system is decreased, the heat releasing reaction, namely the exothermic reaction, will be favored. So we observe these two very important parts here. So now it's time to move on out of this basic theory part. The effect of temperature on the system of nitrogen dioxide and dinitrogen tetroxide. This demonstration will investigate the effect of temperature on the following equilibrium system. If a sample of NO2 gas is taken, it exists in a mixture of NO2 and N2O4. Normally, students, when you produce a sample of NO2 gas and then if you take it into a vial, after a while it automatically develops an equilibrium between NO2 and N2O4. So the equilibrium is given here and its enthalpy value is also given here. You can see the forward reaction is an exothermic reaction here because the forward reaction enthalpy change is a negative value, meaning the forward reaction is exothermic and the reverse reaction is endothermic. So nitrogen dioxide gas is a brown color gas. NO2 gas is a brown color gas, whereas the dinitrogen tetroxide is going to be a colorless gas. Dinitrogen tetroxide is a colorless gas. So these two gases have very distinctive colors, which actually helps us in observing the changes that take place when we change the temperature of the system, concentration of the system, or when we change the pressure of the system. This reaction is an exothermic in the forward reaction and endothermic in the reverse reaction. This is because dinitrogen tetroxide is more stable than nitrogen dioxide. So dinitrogen tetroxide or N2O4 is more stable than nitrogen dioxide. The bonds in dinitrogen tetroxide are stronger than the bonds in nitrogen dioxide. That is why we consider dinitrogen tetroxide to be more stable than nitrogen dioxide. So therefore, formation of dinitrogen tetroxide is an exothermic reaction, and again dinitrogen tetroxide turning into nitrogen dioxide, which is going to be a less stable version of it, is going to be an endothermic, energy taking reaction. So whenever you take a more stable substance and turn it into more unstable substance, you have to provide energy. So in this case, it's clear in the forward reaction we release 58 kilojoules of energy per mole, and the reverse direction we absorb 58 kilojoules per mole amount of energy. An increase in temperature will cause the reaction to shift in a way that uses excess heat. an increase in temperature will cause the reaction to shift in a way that uses heat or excess heat, which means it favors the endothermic reaction in simple words. While the decrease of temperature will result in shift of the equilibrium position to produce heat or favors the exothermic reaction. So to observe these changes, we have to first prepare a sample of nitrogen dioxide. So we know when we lower the temperature, exothermic reaction will be favored. When we elevate the temperature, the endothermic reaction will be favored. So now we have to observe whether these theory parts that we discuss can actually be observed practically in the lab. So that's what we are going to do. We are going to first collect a sample of nitrogen dioxide gas and elevate the temperature of the system, and then reduce the temperature of the system to observe whether the forward reaction or the reverse reaction is going to be favored when we change the temperature. Preparation of nitrogen dioxide gas. Add about 5 grams of copper turnings into a boiling tube and add about 5 cubic centimeters of concentrated nitric acid. So if you react copper turnings or copper metal with concentrated nitric acid, you will produce nitrogen dioxide, water and copper nitrate. Nitrogen dioxide, water and copper nitrate. Nitrogen dioxide gas produced will very clearly be seen because of the red-brown color that can be observed when the nitrogen gas is produced. Nitrogen gas, students, have a red-brown color, so you can very clearly observe this when the nitrogen gas is being produced. So we are going to use this particular reaction to produce the nitrogen dioxide gas. We need to carry out this experiment. Preparation of nitrogen dioxide, dinitrogen tetroxide, gaseous equilibrium system. So we initially produced nitrogen dioxide, but to carry out this experiment we need an equilibrium or equilibrium system. So in this part we are going to learn how to produce this equilibrium system. Add about 5 grams of copper turnings into a boiling tube and pour approximately 5 cubic centimeters of concentrated nitric acid into the boiling tube. Immediately connect the delivery tube to the boiling tube to collect the evolved gas. So we will add copper turnings and nitric acid together, and immediately the gas produced will be delivered through a delivery tube into another boiling tube. Ensuring that the gas is collected into 3 identical test tubes to maintain uniformity in color intensity. Securely seal the test tubes with rubber corks to prevent gas leakage. So students, when the gas is being produced with the help of a delivery tube, we can fill them into 3 different test tubes, or if you happen to prefer to use boiling tubes, you can go ahead and do that as well. Right, so you can fill nitrogen dioxide gas all the way to the top of the test tube or the boiling tube, and we can quickly secure a rubber cork on the boiling tube or the test tube to make sure that no nitrogen dioxide gas is escaping the system. So after a while, when you carry out this experiment, you will be able to collect nitrogen dioxide gas into 3 different boiling tubes or test tubes. They will appear red-brown in color. If you have collected equal amounts of nitrogen gas, approximately the same amount of nitrogen gas into each vial, the color intensity of each of the vials will be the same. So right now, students, since we have produced an enclosed system here, within this enclosed system, nitrogen dioxide will turn into dinitrogen tetroxide, and dinitrogen tetroxide again will come back into nitrogen dioxide. So what have we produced here? We have produced an equilibrium system where the forward reaction as well as the reverse reaction is happening. If they have obtained the equilibrium, the forward reaction rate and the reverse reaction rate will be the same. Right, so we have produced these three equilibrium systems. Now this is the equation. Again, we are taking a look at the equation between nitrogen dioxide and dinitrogen tetroxide. Nitrogen dioxide is brown in color or red brown in color, and dinitrogen tetroxide is going to be colorless. After the production of nitrogen dioxide gas, collect the gas into three boiling tubes, label them A, B and C. A, B and C has the same amount of nitrogen dioxide that is collected into them, and therefore the gaseous system will display similar red-brown color with the same color intensity. So this is a very important point. After collecting nitrogen dioxide gas into whichever the vial that you want to collect them into, preferably a boiling tube or a test tube, all three of these vials that you collect nitrogen dioxide to should have the same color and the same color intensity. So all of them should appear red-brown in color, and the color intensity of each of the vials, or red-brown color intensity of each of the A, B and C vials should be the same. If they are not the same, then we cannot carry out a proper comparison when we are subjecting different vials into higher and lower temperatures. So students, when you are carrying out this experiment, take precaution to collect the correct amount of nitrogen dioxide into each of the vials. So at the end of producing the equilibrium, you will see each of the vials A, B and C will have the same color, as well as the same color intensity will be observed. While maintaining A as a control, system B is partially submerged in an ice bath, while system C is partially submerged in a hot water bath. So we have our system A, B and C. System A, B and C. Now we keep A as our control, so we do not do anything to it. We leave it in the room temperature pressure conditions. We do not tamper with it. However, we are going to place system B in an ice bath and system C in a hot water bath. So we are decreasing the temperature of system B while increasing the temperature of system C. So when you do this, students, you will observe a color change. Do you see system A has a moderate red-brown color and system B now has a lighter red-brown color. So this diagram indicates what will happen when you add system B to an ice water bath. That means we are lowering the temperature. So when you are lowering the temperature of this equilibrium system, the color intensity that is observed in the system B will decrease. Now this color is there due to the presence of nitrogen dioxide gas. So if the color decreases, the color intensity decreases in system B, that would mean the nitrogen dioxide concentration is going down. So when we lower the temperature, nitrogen dioxide concentration goes down and dinitrogen tetroxide concentration has gone up. So when we increase the temperature, if you observe, you can see the color intensity of this red-brown color has increased in system C. When we increase the temperature, the red-brown color intensity has increased. So why would the color intensity increase when we increase the temperature? Or what is the reason for this red-brown color to be more prominent here? Because the nitrogen dioxide concentration within this vial has now increased. That means when we increase the temperature of the system, one forward or the reverse reaction has been favored. Due to that, the nitrogen dioxide gas has been produced more, which increases the concentration of nitrogen dioxide. So to be very precise, the reverse reaction has been favored when we increase the temperature, leading to a higher concentration of nitrogen dioxide, meaning a higher color intensity or greater color intensity. So this set of pictures should be very clearly communicating to you what happens when we submerge one vial in cold water, or when we lower the temperature, as well as when we elevate the temperature. So let's take a look at what happens one step at a time. Decreasing the temperature of the equilibrium system. Compared to the system A, temperature of system B is low. As we can see over here, compare system A is at room temperature, system B is at in a lower temperature because we are using ice bath here. The temperature of system B is low. The color intensity of system B is less than the color intensity of system A. So we have this equilibrium students. We can say that nitrogen dioxide is red brown in color, dinitrogen tetroxide is colorless, and the enthalpy value for the forward reaction is a negative value, meaning forward reaction is exothermic, the reverse reaction is endothermic. Since the color intensity of B has decreased, it can be concluded that the concentration of nitrogen dioxide has decreased while the concentration of dinitrogen tetroxide has increased. So we can assume the reason for the color to be different in ice water bath is because the nitrogen dioxide concentration has gone down. So that means nitrogen dioxide has gotten used up in this equilibrium more and more. That means the forward reaction was favored, producing more and more dinitrogen tetroxide. Because of that, students, we can say N2O4 concentration is going up, NO2 concentration has gone down. This means that the equilibrium position shifted to the right. Equilibrium position shifted to the right when the temperature of the system was reduced. So it's very clear, students. We can see since the N2O4 concentration went up while the NO2 concentration went down, the equilibrium position has shifted to the right. So what caused this equilibrium position shift? Lowering the temperature of the system. Lowering the temperature of the system has caused the equilibrium position to shift to the right. Why? Because the forward reaction is exothermic. So when we try to decrease the temperature of the system, the exothermic reaction will be favored. That is why equilibrium position has shifted to the right, because the forward reaction was exothermic. So momentarily the forward reaction was favored. Therefore, the N2O4 concentration went up, causing the equilibrium position to shift to the right. Explaining with the use of Le Chatelier's principle, when the temperature of the system is lowered, according to the Le Chatelier's principle, the exothermic reaction will contribute to increasing the temperature of the system should be favored. So according to the Le Chatelier's principle, when you lower the temperature of the system will try to increase the temperature by favoring the exothermic reaction. In this equilibrium, the forward reaction is exothermic. So forward reaction was favored. And that is why the concentration of N2O4 was increased. So again, what I mentioned earlier is mentioned here as well. Since the above reaction's forward reaction is exothermic, the forward reaction should be favored. Due to this, the concentration of the products will increase while the NO2 reactant concentration decreases. We discussed this earlier. Due to the changes of the concentration mentioned above, the red-brown color of solution or of system B, not solution B, it's system B, will decrease. So we are dealing with gaseous systems here. So when the NO2 concentration goes down in this gaseous system, the color associated with NO2 will decrease. Due to lowering of temperature of system B, equilibrium was disrupted initially. So that is the first thing that happens. When you lower the temperature, the equilibrium that they already have will be disrupted. And a new equilibrium was formed at the lower temperature it was subjected to. The equilibrium position we saw has shifted to right when establishing the new equilibrium. So students, when products are produced more, or when compared to the initial equilibrium, if the product concentration has gone up, then we say equilibrium has shifted to the right hand side. Compared to the initial equilibrium, if the second equilibrium has produced more and more reactants, we can say equilibrium has shifted to the left, right? So we have to keep in mind, in this case, we have produced more and more products. That means equilibrium position of the system has now shifted more towards the right hand side. Now what happens if you increase the temperature of the system? So we will compare system A with system C. When comparing the system A and system C, the temperature of system C is higher. Yes, we place system C in a hot water bath. The color intensity of the red-brown color observed in system C is higher compared to system A. So we can see when we place the system C in a hot water bath, the color of the system C, actually the color intensity of system C increased. It became higher compared to system A. System A was our control. In this case, when we increase the temperature of the system, according to Le Chatelier's principle, the system will try to decrease the temperature, meaning the endothermic reaction will happen more, right? So if the forward reaction of this equilibrium is exothermic, then the reverse reaction is endothermic. So meaning when you increase the temperature of the system, the endothermic reaction, heat absorbing reaction, will happen more in the hopes of cooling down the system. So students, when we increase the temperature, the reverse reaction will be favored. It will be favored momentarily until the new equilibrium is obtained. Until the new equilibrium is obtained, the reverse reaction rate will be higher momentarily or temporarily higher compared to the forward reaction rate. So this small time period, the forward reaction rate will be smaller than the reverse reaction rate. So the reverse reaction rate will be greater, meaning more and more products will turn into reactants than reactants turn into products. That means compared to the initial equilibrium, reactant concentration will go up, product concentration will come down. So we say equilibrium has shifted to the left, more towards the products side. The reverse reaction above, equilibrium is endothermic. When the temperature of the system C is increased, according to Le Chatelier's principle, the heat absorbing endothermic reaction will be favored, causing the NO2 concentration to be higher and the equilibrium position to shift to the left when the new equilibrium is established. Due to the increase of NO2 concentration in the new equilibrium, the red-brown color intensity will be greater compared to system A. Now system A is still in the initial equilibrium. We didn't do anything to system A. But when we subject system C into higher temperatures, we saw due to high temperatures, temporarily the reverse reaction was favored, causing the equilibrium position to shift to the right at that new temperature. So at this point, due to NO2 being produced more, the color intensity of system C will be higher. The influence of temperature on equilibrium. The changes of concentration that take place when the temperature of NO2, N2O4 system is changed are given below. So you can see here there are two graphs drawn for system A and system B and system C. So this is temperature is increased. This is what happens when the temperature is decreased. So when you increase the temperature, when the temperature is increased, you can very clearly see that now we have N2O4 as a product, NO2 as a reactant. We can see when you increase the temperature very quickly, NO2 concentration has gone up, N2O4 concentration has come down. But after a while, they both have these graphs both have plateaued, or they will not show any change after a while when the second equilibrium is obtained. So at point at which their concentrations no longer change, that means this point, it will no longer change its concentration, meaning they have obtained a new equilibrium. So one thing to notice is, earlier the N2O4 concentration was higher, but when we all of a sudden change the temperature by increasing the temperature, you can see the N2O4 concentration quickly, within a short period of time, decreased while producing more and more NO2. So establishing this new equilibrium did not take that long. It happened within a short period of time. As we know, when you increase the temperature of a system, both of the reactions rates will be increased. Both forward and reverse reaction rates will be increased. However, the endothermic reaction rate will increase more compared to the reverse reaction rate. So you can see very clearly you have a sudden decrease of N2O4 and increase of NO2, but after a while the forward reaction rate and the reverse reaction rate will be equal to one another. At that point, we will see no change in the concentration of NO2 or N2O4 until the reaction rates become equal to one another once more. You will see an increase in NO2 concentration and decrease in N2O4 concentration. Now, why is N2O4 getting used up more here? As we know, when we increase the temperature, the reverse reaction was favored and the equilibrium position was shifted to the left. So therefore, students, we can see more and more reactants being produced. So therefore, product concentration goes down, reaction concentration goes up. Over here, you can very clearly see, now this is when the temperature was decreased. Now here you can see the new equilibrium. So whenever the concentration of nitrogen dioxide and dinitrogen tetroxide does not change, that means we have obtained equilibrium. So if we are being very specific about this, at this point we can say a new equilibrium was obtained. At that particular point, we can say a new equilibrium was obtained. You can draw it like this. At this point, a new equilibrium was obtained and the temperature was changed at this point. So a very short period of time, we can say it took very short period of time for the new equilibrium to be obtained when the temperature was increased. Over here, the temperature change was brought about around this point, and we can see both of the concentrations start not changing anymore around this point. Right? At that point, you can see the concentration of N2O4 is no longer increasing and concentration of NO2 is no longer decreasing. So that means it took this many seconds for the new equilibrium to establish. So compared to the previous graph, you can very clearly see it has taken a longer period of time for the new equilibrium to establish. Now, why is this? Now, this is because we have lowered the temperature. So the reaction rates are low and it takes a while for the reaction rates to be equal to one another as well. So the establishing of the new equilibrium will take a little while longer compared to the system C. System C was placed at a higher temperature. So at a higher temperature, due to rates being somewhat higher, the new equilibrium will be established in a relatively shorter period of time compared to when the temperature is decreased. However, here as well, you can very clearly observe, that when the temperature was changed, you can see the nitrogen dioxide concentration has gone down. Nitrogen dioxide concentration has gone down, while dinitrogen tetroxide concentration has gone up. So nitrogen dioxide is the reactant, dinitrogen tetroxide was the product, and we saw the forward reaction was exothermic. So when we decrease the temperature, the exothermic reaction will be favored, meaning nitrogen dioxide concentration goes down while dinitrogen tetroxide concentration goes up. So that is what has happened. At one point, you can see the concentrations of both the reactants and products do not change, meaning we have obtained a new equilibrium. And you can very clearly see, to obtain the new equilibrium, it took a longer period of time for the system B, the system that was cooled. So when the temperature was lowered, it takes a longer time for the new equilibrium to be obtained, because both the reverse and the forward reaction rates are decreasing. However, the exothermic reaction was favored. So exothermic forward reaction was having a higher rate compared to the reverse reaction. Explaining the influence of temperature on equilibrium. When the temperature is increased, the endothermic reaction will be favored and the equilibrium position will be shifted to the left. Now we have discussed this in great detail in the previous slides as well. This causes an increase in NO2 concentration while decreasing the concentration of N2O4. So we can very clearly see N2O4 concentration has gone down. It has gone down and NO2 concentration has gone up. And this has happened in a fairly short period of time. When you decrease the temperature, the exothermic reaction will be favored and the equilibrium position will be shifted to the right. This means decrease of NO2 concentration will happen while increasing the concentration of N2O4. You can very clearly see this red color line indicates the concentration of NO2. NO2 concentration has gone down while N2O4 concentration has gone up. NO2 concentration goes down, N2O4 concentration goes up. This is due to favoring the forward reaction, which happens to be exothermic. When observing the above graphs, it can be observed that when the temperature is increased, the system has reached equilibrium in a very short period of time. Yes, we observed that earlier as well, right? So we can see if this is the point at which the change starts to happen, we can see in a very short period of time. I'll use a different color so that you can see it clearly. If we use different color, maybe something like green. You can see in a very short period of time, a new equilibrium has established. Over here, we can see this is the point at which we start making the temperature change, and around here is a point at which we see that the concentrations of NO2 and N2O4 does not change. So when the concentrations of these two things do not change, we can be sure that the forward reaction rate and the reverse reaction rate is the same, meaning at that point a new equilibrium is established. So you can see the gap over here, or the time it took over here to establish the new equilibrium. It is much greater than the time it took for this system to establish a new equilibrium. So at higher temperatures, the equilibrium was established faster, but when the temperature was lowered, it took a longer period of time to establish the new equilibrium. One observation that you have to make. However, when the temperature was decreased, the system reached a new equilibrium much slower compared to when the temperature was increased. The rate of reactions when temperature was increased was higher than the rate of reactions when the temperature was lowered. So when the temperature was lowered, the rate of reactions also get lowered. When temperature is increased, the rate of reactions will increase. But students, when you're answering questions, when you want to answer what happens in the system according to Le Chatelet's principle, you have to state which reaction is going to be favored. Now, again, very important detail to keep in mind is when we increase the temperature of a system, both the forward and the reverse reaction rate will increase. Now, if you can't wrap your head around that fact, think about something like this. Imagine a reaction that is not considered to be an equilibrium reaction. Imagine a unidirectional reaction where reactants convert directly only into products. Now, you know, in such a reaction as well, usually when you increase the temperature, the reaction rate will increase, regardless of whether the reaction is exothermic or endothermic. So, students, just like that, when you take an equilibrium reaction as well, if the system's energy, or if you provide the system more and more energy, at that point, both the forward reaction rate as well as the reverse reaction rate will increase. Both the forward and the reverse reaction rates will increase. However, when you increase the temperature, according to Le Chatelet's principle, we know they will try to bring down the temperature of the system. So, an equilibrium system, you can do that by favoring the endothermic reaction. Endothermic reaction is the reaction where they absorb energy. So, we provide the system energy by heating the system, and the system will absorb that energy and turn into or carry out more and more of the endothermic reaction. Right, so when we provide the system more energy, endothermic reaction will happen more and will remove some of the additional energy we provide to the system. So students, does that mean that the exothermic reaction is not happening? Does that mean the exothermic reaction rate has to be lowered? No. Actually, when you increase the temperature, both the reaction rates will increase, but compared to the exothermic reaction rate, endothermic reaction rate will be higher. However, as time passes by, both of these reaction rates will be equal to one another. So there will be a time where both of the reaction rates will be equal to one another, and at that point, the second equilibrium or the new equilibrium will be obtained. So keep in mind, we have an equilibrium that already has an established equilibrium, and then we change its temperature. At that point, when you increase the temperature, both the reaction rates will increase, but one will increase more than the other. So after a while, both the reaction rates will come and be equal to one another, and at that point, we obtain our new equilibrium. So keep that in mind, very important detail. We will take a look at the graphs as well, so that you develop a better understanding of what we discuss here. We have the below graphs can also be used to show the effect of temperature on the equilibrium above. So let's take a look at the graphs as well. So these two graphs also represent what happens when we increase the temperature of system C as well as decrease the temperature of system B. So on my left hand side, what we have over here is increasing the temperature related graph, and on my right hand side we have decreasing the temperature related graph of system B. So this is what happens to system B. This is what happens to system B. This is what happens to system C. Right. So now you can very clearly see here, when we increase the temperature, now imagine we started increasing the temperature at this point, when time was 0. Let's say we increase the temperature. So we can see at one point, now we will see first of all the nitrogen dioxide concentration will go up, and we discussed this in detail earlier as well. When we increase the temperature, the reverse reaction will be favored, so therefore nitrogen dioxide concentration will be going up. But at one point, we can very clearly see at this point, the nitrogen dioxide concentration has gotten to a constant value. From that point onwards, we don't see an increase in nitrogen dioxide concentration. We can say the same about dinitrogen tetroxide or N2O4 concentration as well. After reaching this T1 point, the concentration of that has not changed. Why is this? This is because at that point, the forward reaction rate equates the reverse reaction rate. Both the forward reaction and the reverse reaction now has the same rate. So when certain amount of reaction molecules convert into products, the same number of product molecules come back into produce the or replace the lost amount of reactants. So the reactant and the product concentrations do not change. So students, this is a T1 value, the time value. Let's say in time in seconds. Here we have a T1 amount of seconds spent to obtain this equilibrium. So again here, if you observe, when we decrease the temperature, we can very clearly see again at this point we have obtained the new equilibrium. We can see from this point onwards the N2O4 concentration hasn't changed, as well as NO2 concentration hasn't changed, meaning from this point onwards we have obtained the new equilibrium. So to obtain the new equilibrium, it has taken T2 amount of time. So here we can very clearly see that the T2 is greater than T1. The time taken for obtaining the equilibrium in a higher temperature was smaller than obtaining an equilibrium at a lower temperature. So this is one thing that you need to observe here. So T1 is smaller than T2. Let's read the given text here. The above graphs show how the system has reached dynamic equilibrium when temperature is altered. So another very important word is this dynamic equilibrium. Now students, dynamic equilibrium means it is not a static equilibrium, where in a dynamic equilibrium always the forward reaction as well as the reverse reaction is continuously happening. Right, so we know 2 nitrogen dioxide get used up to produce 1 N2O4 or 1 dinitrogen tetroxide. So if the rate of the forward reaction as well as the reverse reaction is exactly the same, simultaneously when 2 nitrogen dioxide is getting used up to produce 1 dinitrogen tetroxide, 1 dinitrogen tetroxide turns back into 2 nitrogen dioxide. So meaning this process happens simultaneously all at once. So because of that, when the forward reaction as well as the reverse reaction is happening, the concentration of the nitrogen dioxide or the concentration of N2O4 does not change, because the forward as well as the reverse reaction rates remain the same. Right, so because of that, these constant concentration values are not due to the reaction stopping. Reaction is continuously happening. That is why we call this a dynamic equilibrium. If the reaction stops, then it is not a dynamic equilibrium. Here, since the reaction, both the forward reaction and the reverse reaction is continuously happening, but they happen at the same speed. So therefore, at the equilibrium, whichever the concentration of the products as well as the reactants will not change. Whatever the concentration they may be, they will not change. Doesn't mean that they are equal to one another. The concentrations of reactants and products are not equal to one another. However, whatever the concentrations they have at the time they obtain the equilibrium will no longer change after obtaining the equilibrium. So we observe how the temperature affects the equilibrium. However, first of all, after going through this sentence, we'll have another paragraph to read. However, when the temperature was decreased, both the forward and the reverse reaction slowed down and therefore reached a new equilibrium after a considerably longer period compared to when the temperature was increased in the system. So when you lower the temperature, both the reaction rates slow down. So they'll take a longer period of time to obtain the equilibrium. When the temperature is increased, both the reaction rates are increased, so they will quickly obtain a new equilibrium as well. So T1 is smaller than T2 due to that reason. The effect of concentration on equilibrium. So we are moving on to a new factor now, concentration. So we have this equation. Now always keep in mind, according to Le Chatelier's principle, when we try to increase something, the system will try to decrease it. When you try to decrease something, the system will try to increase it. Adding more nitrogen dioxide gas. When nitrogen dioxide gas is added to the above equilibrium system, nitrogen dioxide gas concentration will instantly go up. According to the Le Chatelier's principle, the system will try to obtain a new equilibrium by reducing the NO2 concentration by shifting the equilibrium to the right. So students, if you increase the concentration of NO2, system will try to decrease the NO2 that is added to the system additionally. So when you increase the NO2 concentration, system will try to decrease the NO2 concentration. So when we try to decrease the NO2 concentration, that means the forward reaction should be favored, or the forward reaction has to happen more and more, which would mean the N2O4 concentration will eventually go up. When the forward reaction is favored, the N2O4 concentration will be increasing. So students, we can say at this point, due to the addition of excess or additional NO2, the forward reaction was favored. So whenever the forward reaction is favored, the equilibrium position will shift to the right, or in the forward direction, meaning towards the right. So equilibrium position will shift to the right. So you can see over here, we can observe what has happened in the graph. We have N2O4 concentration, NO2 concentration. So this period is the period where we have our usual equilibrium before we made any changes to the equilibrium. So at time t1, we have added new NO2. We have added additional amount of NO2 into the system. So you can see NO2's concentration quickly goes up due to the change we make. Now the system tries to bring down that change by carrying out the forward reaction more and more. So whenever there's a higher concentration of NO2, the forward reaction will anyway automatically increase due to having a higher concentration of NO2 now. So the forward reaction rate will increase. So as the forward reaction rate increases and carries out the forward reaction, the NO2 concentration decreases. Why? Now there's a higher speed of converting NO2 into N2O4. Forward reaction has a higher rate. So the reactant concentration will gradually decrease. You can see it here. But as the reactant concentration gradually decreases, we know little by little the product concentrations will go up, because we are now producing more and more products faster. So when the product concentration goes up, even the reverse reaction will gradually increase. So forward reaction rate will initially automatically be increased to a higher level, but as time passes by, the forward reaction rate will come down. And the reverse reaction rate initially will be quite small, but when the when the products get produced more, even the reverse reaction rate will gradually increase. So at one point, the reverse reaction rate as well as the forward reaction rate will be equal to one another. At that point, a new equilibrium will be obtained. So you can see when the new equilibrium is obtained at T2, we can very clearly see NO2 concentration no longer changes, as well as dinitrogen tetroxide concentration no longer changes. Now you can very clearly see what I mentioned earlier as well. As we increase the NO2 concentration by adding nitrogen dioxide here, at this point the forward reaction rate must be quite high. So when the forward reaction is carried out at that rate, we will quickly decrease the concentration of NO2, because forward reaction rate is quite high, so the reactants are getting used up faster. So then little by little the reactant concentration goes down. As the reactant concentration goes down, even the forward reaction rate will come down little by little. So the forward reaction rate will also slightly decrease. But as the forward reaction produces more and more products, the reverse reaction rate will also increase. You can see the product concentration is increasing. When the product concentration is increasing, the reverse reaction rate will increase. So the forward reaction rate comes down, product concentration increases, so therefore reverse reaction rate will increase. At one point, these rates will be equal to one another. So at that point, you can see the N2O4 concentration and the NO2 concentration will no longer change. Whatever the concentration values that they have, the point at which they obtain the new equilibrium will no longer change due to forward reaction being equal to the reverse reaction rate. So at T2, we can say a new equilibrium is obtained. So this is how the graph will appear when we add additional amount of nitrogen dioxide to the equilibrium mixture. All of a sudden the concentration will increase and it will gradually come down and it will plateau after a while. And here also you can see nitrogen dioxide concentration or N2O4 concentration will gradually increase and eventually it will come to a constant value. At T1, the nitrogen dioxide concentration was suddenly increased. At T2, a new equilibrium was obtained. During the time between T1 and T2, the NO2 concentration decreases. However, the concentration of NO2 at the new equilibrium is greater than the concentration of NO2 in the initial equilibrium. Very important observation, students. Now, we can see, yes, Le-Chatelier's principle will try to counter the changes we make. However, in an equilibrium system, when we add something to it or when we make any changes to it, the equilibrium system will no longer be able to go to the original equilibrium where the concentration of NO2 and N2O4 was at these initial values. You can't bring the concentration of NO2 to the initial value, or you can't bring the concentration of N2O4 to the initial value. However, we will try to change the equilibrium to reduce the change that externally was made to the system. Externally we added a lot of NO2, but system tried to decrease it, so it has decreased the NO2 concentration, but it can't decrease the NO2 concentration all the way down to the initial concentration value. That is not possible, right? So even the NO2 concentration here is slightly higher than the initial NO2 concentration. During this time, the N2O4 concentration will increase, and the N2O4 concentration at new equilibrium is greater than the initial concentration of the NO2 in the equilibrium system. So initially, certain additional amount of NO2 was added, and as this paragraph explained, that added amount of NO2 caused a change in the equilibrium, and this favors the forward reaction, producing an additional amount of N2O4, right? So the N2O4 concentration in the new equilibrium is not going to be the same as the N2O4 concentration in the initial equilibrium. If the equilibrium constant is Kc, it will be equal to N2O4 gas concentration divided by N2O or NO2 gas concentration to the power 2. Now we can write the equilibrium constant based on this equation here. So you can see product concentration divided by reactant concentration, and each of these concentrations are raised to their stoichiometric coefficients as their powers. Right. In the first equilibrium also we have this equilibrium constant. In the second equilibrium also we have the same equilibrium constant. However, students, the Kc values in both of these, are they different or are they the same? Now you have to know, you have to remember, when it comes to equilibrium constant will only change with temperature. Meaning, if you change the reactant or the product concentrations of any equilibrium, although the equilibrium position will shift, it will not change the equilibrium constant value. If the reaction is carried out in the same temperature, changing the concentration of each of the reactants or products will not alter the equilibrium constant for that given reaction. In the above equations written, the concentration of N2O4 in the second equation is greater than the concentration in the first equation, and the concentration of NO2 in the second equation is less than the first. So we can see here in the first equation, N2O4 as well as NO2 concentrations are going to be smaller than the concentrations of NO2 and N2O4 concentration. So in expression 1, both of these reactants and product concentrations are going to be smaller than the reactant and product concentration of the second expression. However, since the temperature was kept a constant, the Kc value in both instances will be the same. So students, the Kc value will not change. You will see if you carry out this reaction and find out the concentrations of each of these reactants and products in two different situations where we have changed the concentration. You can see if the temperature was kept a constant, whenever you carry out an experiment like this to find out the Kc value, in both of the instances, the Kc value will be the same. However, if you change the temperature, at that point, Kc value will change. So Kc value or the equilibrium constant will only change with temperature. When the concentrations are changed in the above equilibrium system, the equilibrium position will change. However, equilibrium constant will not change. Yes, equilibrium position can change. Equilibrium position can change. However, equilibrium constant will not change. That is something that you need to keep in mind. Now we take a look at another situation where we remove NO2. So what will happen if you remove NO2? Due to the removal of NO2, the concentration of NO2 will suddenly drop. At this point, according to the Le Chatelier's principle, the reaction that produces NO2 will be favored, and therefore the reverse reaction, in this case this reverse reaction will be favored. So this will shift the equilibrium position to the left. So this we have explained many a times what happens. Le Chatelier's principle mentions when you are making a change to the system will try to oppose that. So you can very clearly see when you remove NO2, system will try to produce more and more NO2. Will the system be able to produce NO2 all the way up to the initial concentration of NO2? No. However, system will try to increase the NO2 concentration and minimize the change that externally was brought about. So when you decrease the concentration of NO2, the N2O4 will convert more and more into NO2 until a new equilibrium is going to be established. That means the reverse reaction will be favored and the equilibrium position will be shifted to the left. So you can see a sudden decrease in concentration of NO2 will take place, and gradually, since the reverse reaction is favored, gradually the forward NO2 concentration will increase. At one point, the reverse reaction as well as the forward reaction rate will be equal to one another. At that point, a new equilibrium will be obtained. So T2 denotes the time that produces the new equilibrium. At T1, the concentration of NO2 is reduced. From T1 to T2, the initial equilibrium changes to obtain a new equilibrium at T2. Although NO2 concentration increases from T1 to T2, the NO2 concentration at the new equilibrium is going to be smaller than the concentration at the initial equilibrium. So you can see very clearly here, this equilibrium concentration, the second equilibrium NO2 concentration is smaller than the initial concentration of NO2 or initial equilibrium NO2 concentration. So students, although the Le Chatelier's principle suggests that system will try to decrease or minimize the change that we do to the system, it can't completely recover from the changes we make. changes in the rate of reaction when the concentration of an equilibrium system are changed. First one, reducing the NO2 concentration. Now, at this point, we are going to be observing the rate, or how the rate of each of the forward and the reverse reactions will change when we reduce the NO2 concentration of the equilibrium system. So, first of all, before we look into this, in this case, RF stands for the rate of the forward reaction, RB stands for rate of the backward or the reverse reaction. So, in this particular graph, we can see the y-axis is rate and the x-axis is time. So, you can see in the initial equilibrium, both the forward and the reverse reaction rates are the same. RF and RB are equal to one another. Then at T1, when time is equal to T1, we reduce the NO2 concentration. Now, NO2 is the reactant, N2O4 is the product. So, that means the forward reaction rate should decrease. Why? When we decrease the NO2 concentration, if you can't remember the equation, we will write it down here. NO2 turns into N2O4. So, at T1, when we remove NO2, there will be a sudden drop of the NO2 concentration, or there will be a sudden drop in the NO2 concentration. So, at that point, students, when the concentration of a particular reactant goes down, we know that reaction rate will drop. So, you can see, since NO2 is a reactant for the forward reaction, the forward reaction rate has come down drastically. Compared to that, the reverse reaction rate still stays the same. We can say reverse reaction rate is much higher now compared to the forward reaction rate. So, therefore, reverse reaction will happen a bit more faster, or the reverse reaction rate is greater. So, therefore, conversion of this N2O4 into NO2 is going to be happening at a much higher rate compared to the conversion of NO2 to N2O4. So, that means this reaction rate will be faster. So, more and more NO2 will be produced faster. So, you can see gradually the forward reaction rate starts to increase. Now, why is that? Because when more and more NO2 is getting produced, so the NO2 concentration will gradually increase again. So, when the NO2 concentration increases, the forward reaction that depends on the NO2 concentration will also have a higher rate. So, forward reaction rate depends on the NO2 concentration. As soon as the NO2 concentration goes down, the reverse reaction rate will be higher compared to the forward reaction rate at that point. So, therefore, more and more N2O4 will dissociate and turn into NO2. Right, so NO2 concentration will be higher at that point, or will gradually become higher. So, then when the NO2 concentration gradually becomes higher, the forward reaction that depends on the NO2 concentration will gradually increase. Now, as I mentioned earlier, as soon as the NO2 concentration went down, the reverse reaction rate was greater. So, therefore, reverse reaction is happening faster. Due to this, N2O4 concentration decreases, because now N2O4 is getting used up faster than it is getting produced. So, N2O4 is getting used up faster than it is getting produced. So, therefore, N2O4 concentration gradually decreases. So, when the N2O4 concentration gradually decreases, the reverse reaction that depends on the N2O4 concentration will have a smaller and smaller rate. The rate of the reverse reaction will gradually decrease. So, you can see here, rate of the reverse reaction gradually decreasing, while the rate of the forward reaction gradually increases. So, at one point, students, this reverse reaction rate and the forward reaction rate will be equal to one another. And at that point, a new equilibrium will be obtained, because at that point onwards, the forward reaction rate will be equal to the reverse reaction rate. So this is how the new equilibrium is going to be obtained, students. As soon as we reduce the NO2 concentration, the forward reaction that is affected by the NO2 concentration will quickly have a very smaller rate, or the forward reaction rate will quickly drop. And at that point, the reverse reaction rate will be much higher than the forward reaction rate, meaning reverse reaction will be producing more and more NO2 faster. So gradually NO2 concentration will go up. Because of that, the forward reaction rate will gradually come up. Since the N2O4 is now getting used up faster, the reaction that depends on the N2O4 concentration, which is the reverse reaction rate, will decrease. Reverse reaction rate will decrease. Forward reaction rate will increase, the reverse reaction rate will decrease. At one point, the forward reaction and the reverse reaction rate will be equal to one another. At that point, we say a new equilibrium is established. Due to the decrease in NO2, due to the decrease in NO2 concentration, the rate of the forward reaction will suddenly be lowered. However, due to the reverse reaction being favored, the NO2 concentration will gradually increase while the N2O4 concentration gradually decreases. So we know, according to Le-Chatelier's principle, we can say the reverse reaction was having a higher rate to counter the change that has happened here. Due to the gradual increase of NO2 concentration, the forward reaction rate will increase. Forward reaction rate will gradually increase. Simultaneously, meaning at the same time, due to the decrease in the concentration of NO2, the reverse reaction rate will gradually decrease from T1 to T2. Reverse reaction rate is starting to decrease, forward reaction rate is starting to increase. At T2, the forward reaction and the reverse reaction rate will be equal to one another, and this will result in obtaining a new equilibrium. As I mentioned earlier, forward reaction rate will increase, reverse reaction rate will decrease, but at one point they will be equal to one another. At that point, the new equilibrium will be established. Increasing the NO2 concentration. So students, when we increase the NO2 concentration, the system, according to Le-Chatelier's principle, will try to decrease the NO2 concentration by favoring the forward reaction. Right? We have a lot of NO2, that means the forward reaction is going to be favored to decrease the NO2 concentration. So let's see what happens in the rate. So you can see initial equilibrium, forward and the reverse reaction rates are the same, but as soon as we increase the NO2 concentration, the forward reaction, which actually depends on the NO2 concentration, will all of a sudden now have a higher rate. So it will start having higher rate and will quickly turn NO2 into N2O4. That means very rapidly NO2 is now getting turned into N2O4. That means NO2 concentration is going down. As the NO2 concentration goes down, what happens to the rate? Rate of the forward reaction will also come down, because the rate of the forward reaction will depend on the NO2 concentration. So if the NO2 concentration goes down, rate of the forward reaction will also come down. But when NO2 is getting turned into N2O4, gradually the N2O4 concentration goes up. Now N2O4 concentration is important for the reverse reaction. Reverse reaction rate will depend on the N2O4 concentration. As the N2O4 concentration happens to increase from T1 to T2, the reverse reaction rate will also increase. So that is what has happened here. As you initially increase the concentration of NO2, you can very clearly see there's a sudden increase of the forward reaction rate, but as the forward reaction happens faster, the concentration of NO2 goes down, so therefore gradually forward reaction rate will also come down. But due to producing more and more NO2, the reverse reaction rate will also gradually increase. So at one point the forward reaction reverse reaction rates will increase. At that point, we say a second or new equilibrium is established. So at T1, you can see a new equilibrium has established. When NO2 is added to the equilibrium system, the NO2 concentration will suddenly increase. The forward reaction rate increases when NO2 concentration increases. This is something that we already know, very simple. When the NO2 concentration is increased according to the Le Chatelier's principle, the forward reaction rate will increase, and therefore the NO2 concentration will gradually decrease while the N2O4 concentration gradually increases. In concentration wise, NO2 concentration goes down, N2O4 concentration goes up. So as the NO2 concentration goes down, forward reaction rate also comes down. As N2O4 concentration comes up, reverse reaction rate comes up. So at one point they will be equal to one another. We will obtain the equilibrium. Due to this reason, the forward reaction rate will decrease with time and the reverse reaction rate will increase. At T2, the two rates will be the same, and at that point, a new equilibrium is obtained. Now, we move on to another important part where we see the effect of concentration on equilibrium when it comes to the products. So, we are going to now add more products or remove some products and see what will happen to the system. Addition of dinitrogen tetroxide N2O4 to the system. When N2O4 is added to the system, the N2O4 concentration will increase. At this point, according to Le Chatelier's principle, the reverse reaction will be favored. Due to this reaction, the NO2 or N2O4 concentration will go down while NO2 concentration increases. Right? So when we increase N2O4 concentration, reverse reaction will be favored, meaning the N2O4 concentration will come down and NO2 concentration will go up. That is very clearly given here. You can see when we add more N2O4, there's a sudden increase of N2O4 concentration, but due to the increase of this concentration, now the reaction will start happen faster, the reverse reaction will start to happen faster. So that means the N2O4 concentration will quickly be brought down little by little. And when that happens, NO2 concentration will gradually increase. And at one point, as we mentioned earlier, the forward reaction and the reverse reaction rate will be the same at one point, let's say at T2. So at that point onwards, the concentration of N2O4 or the concentration of NO2 will no longer change. Between T1 and T2, the reverse reaction rate decreases while the forward reaction rate increases. We know this. And at T2, the two rates will be equal to one another. At that point, we say a new equilibrium is obtained. That is what has happened here. You can see when the concentration of N2O4 is going down, we can assume the reverse reaction rate also gradually decreases and forward reaction rate gradually increases. Now, when you all of a sudden increase the product concentration, the reverse reaction is the one that is going to be favored. So students, the reverse reaction rate will be higher initially, but gradually as the concentration decreases, as given in this graph, this is a concentration graph, as the concentration decreases, the reverse reaction rate will also decrease. But the NO2 concentration keeps on increasing. So therefore, the forward reaction rate will increase. The reverse reaction rate will decrease, forward reaction rate will increase. At one point, the rates will be the same. So therefore, they will establish an equilibrium. So one thing to keep in mind when you're analyzing the concentration versus time graphs, when we have added a reactant or a product to the equilibrium mixture, the new equilibrium established will not have the same concentrations of the reactants and the products. That is something to keep in mind. Here, N2O4 product concentration was increased, but at the new equilibrium, we can very clearly see N2O4 concentration is still higher than the initial equilibrium's N2O4 concentration. It will never be brought down, or it will not be made equal to the initial N2O4 concentration of the initial equilibrium. So that is something that you need to keep in mind. Removal of N2O4 from the equilibrium. When N2O4 is removed from the system, concentration will instantly go down. According to Le Chatelier's principle, the forward reaction will be favored to produce more and more N2O4. So when you remove something, system will try to replace it by, in this case, by producing more and more N2O4. So that means the forward reaction will be favored. So from T1 to T2, the NO2 concentration will decrease while N2O4 concentration increases. You can see very clearly there's a sudden drop of N2O4 concentration because we removed it, but gradually the concentration of N2O4 increases while NO2 concentration decreases, because this decrease is seen because N2O or NO2 is actually getting used up to produce N2O4. So NO2 concentration decreases while N2O4 concentration increases, and at one point their concentrations will no longer change. That indicates that we have established a new equilibrium. When the system reaches an equilibrium at T2, the concentration of N2O4 is smaller than the initial equilibrium concentration, and the NO2 concentration will also be smaller than the initial equilibrium concentration. So one thing to notice is that. So N2O4 concentration as well as NO2 concentration will be smaller compared to the initial equilibrium N2O4 and NO2 concentrations. Right, students, and you can see when in the graph as well, very clearly we have indicated the changes that take place. In O2 goes down while NO2 concentrations increase. Now we turn to observing the effect of pressure. Effect of pressure on an equilibrium system. So we discussed temperature, then we discussed concentration's effect on equilibrium, and now we are going to be talking about effect of pressure in an equilibrium system. Especially when it comes to gaseous equilibriums, effect of pressure is a very important aspect we need to discuss. So let's take a look at increasing the pressure. When the pressure is increased while temperature is kept constant, according to Le Chatelier's principle, system will try to reduce pressure by favoring the reaction that produces a lower number of gas particles, since the number of gas particles are directly proportional to the total pressure of a gaseous system. Now students, in a gaseous system, the pressure that is observed in the gaseous system is due to the gaseous particles colliding with the walls of the container. So more frequent the collisions, the higher the pressure. So the more number of particles that we have in a container, greater the pressure. So when it comes to a gaseous system, higher the number of gas particles or higher the number of gas molecules or number of moles of gas that is present within a system, the higher the pressure. So we can directly say, regardless of the type of the gas that is present in a system, higher the number of gas particles, higher the pressure. So the number of gas particles are directly proportional to the total pressure of a gaseous system. So students, if we increase the pressure of a gaseous equilibrium, the equilibrium will try to decrease the pressure. How can they decrease the pressure? Equilibrium will favor the reaction that produces a lower number of gas particles. Now, if you take a look at this equilibrium as well, in the forward direction, we can see two gas particles are turned into one. So we are lowering the number of gas particles in the forward reaction. In the reverse reaction, you can see one gas molecule is turned into two gas molecules. So when the reverse reaction is happening more, number of gas particles will increase. However, if the forward reaction is happening more, number of gas particles will get decreased. So if we increase the pressure of this system, the reaction that produces a lower number of gas particles will be favored. So in other words, in this particular equilibrium we are dealing with, if we increase the pressure, the forward reaction will be favored, where two gas molecules turn into one. So that means the number of gas particles actually go down in the equilibrium. Due to this reason, the forward reaction will be favored and the concentration of N2O4 will increase while NO2 concentration decreases. Due to this particular reason, the red-brown color intensity of the system will decrease. Now keep in mind, these two gases have very distinct colors. NO2 is brown, actually N2O4 is colorless. So if you increase the pressure of a system like this, you will observe that the forward reaction is going to be favored. So therefore, NO2 concentration will go down and N2O4 concentration will go up. NO2 is the molecule that is responsible for this red-brown color of the system. So when the NO2 concentration goes down, the red-brown coloration of the system will also go down. Now students, we can see what happens when we increase the pressure of a system by halving the volume of a system over here. So we have here a gaseous system, we have halved the volume of that system, and we can see what kind of change takes place in this diagram. So in this particular system, let's say we have a number of NO2 molecules, let's say X amount of NO2 molecules that produces this particular color. However, when you all of a sudden halve the volume of the system, the concentration of NO2 will be doubled, right? The number of NO2 has not changed over here because this is the point at which we initially compress the sample. So therefore, when we initially decrease the volume of the sample, we can see all of a sudden the brown coloration will be having a higher color intensity. So we'll see a bit of a darker brown color here compared to the initial equilibrium mixture. So when you quickly decrease the volume, first observation is a darker brown color because the number of NO2 here and here is the same. Number of NO2 here as well as here is the same. As soon as we change the volume, still a new equilibrium has not gotten established. So over here the number of NO2 is the same as the number of NO2 here, but here the concentration of NO2 is double because now we have half the volume, right? So the concentration of NO2 here is double the concentration compared to the concentration here. So if the concentration of NO2 was, let's say, X, the concentration of NO2 over here will be 2x, right? Number of moles of NO2 in these two places will be the same. So the darker brown color that you observe over here is due to the concentration of NO2 all of a sudden being increased. However, this dark color will not prevail for much longer. As we keep applying the same pressure, this particular pressure, as we keep subjecting the system into that particular new pressure, at that point, a new equilibrium will start to get established. So when the new equilibrium is getting established, as you know, the forward reaction where the number of gas particles decrease will be favored. So therefore, students, NO2 will more and more get converted into N2O4. So because of that, when you go over here, the number of NO2 particles will go down. Number of NO2 molecules will come down. So compared to this dark brown color, at the point at which we obtain a new equilibrium, you will observe a lighter brown color. It will not be the same dark brown color that prevails. Eventually, little by little, the dark brown color will turn into a slightly lighter brown color. It will not be as light as this earlier, although the number of nitrogen dioxide molecules over here, we can say number of NO2 molecules over here will be less compared to the number of NO2 molecules over here. But number of NO2 molecules that we see in this system is spread throughout a larger volume. Here it is present in a smaller volume. So students, keep in mind, although this brown might appear slightly higher than the brown coloration that you see over here, the number of nitrogen dioxide gas here is less, because when we reduce the volume, initially the concentration of NO2 will be doubled, but pressure will also be doubled in this case. So according to Le Chatelier's principle, to reduce the pressure, we are going to favor, according to Le Chatelier's principle, the system is going to favor the reaction that produces less number of gas molecules. That means forward reaction will be favored. So as the forward reaction happens more until a new equilibrium is obtained, we can see number of NO2 molecules in the system will go down. So the coloration, brown coloration, will decrease, resulting in a lighter brown color compared to this situation. We can see a lighter brown coloration compared to this particular instance. So that is something you should keep in mind. You can see when you double the equilibrium's pressure, this is what you observe, and this is the new equilibrium related observation. As soon as the pressure is doubled, not temperature, as soon as the pressure is doubled, an increase in the color intensity can be observed. However, with time, the color intensity will decrease as a new equilibrium is obtained at the new pressure conditions. So we can see in the new pressure conditions, a new equilibrium will be obtained, and in that new pressure conditions, the brown coloration is going to be lighter than the initial observation when we increase the pressure. Alright, so keep in mind, when we initially increase the pressure, there will be a brown coloration, a darker brown color will be observed, but as time passes by, since forward reaction is favored, NO2 concentration will go down, and the brown coloration will be lighter compared to the initial point at which we increase the pressure. Now this slide explains what happens when we lower the pressure. So when lowering the pressure, according to Le Chatelier's principle, the system will try to increase the pressure by favoring the reaction that produces more gas molecules. So according to this, the reverse reaction produces more gas molecules, so the reverse reaction will be favored. So let's read through it. When the pressure is instantly decreased, the red-brown color intensity instantly decreases. Red-brown color instantly decreases. However, after a while, when the new equilibrium is obtained, at the lowered pressure conditions, the color intensity will increase to give moderate red-brown color. According to Le Chatelier's principle, when the pressure of a system is decreased, the reaction that contributes to increasing the pressure by producing more gas particles will be favored. That means the reverse reaction will be which leads to increasing the NO2 concentration will be favored. due to this, color intensity observed in the system will increase. Now students, that is exactly what we can observe in this diagram. Now imagine you have a system where we have nitrogen dioxide and dinitrogen tetroxide, and you can see we can assume that system is dark brown in color, but let's assume that we double the volume and halve the pressure by doubling the volume. So we have decreased the pressure by doubling the volume. So initially, as soon as you do this, the number of nitrogen dioxide particles here, or number of molecules of nitrogen dioxide here, and number of molecules of nitrogen dioxide here will be the same. Instantly when you do this, still nothing has happened to the initial equilibrium, just the fact that the number of molecules of nitrogen dioxide has now gotten spread over a larger volume. So at that point we can see the brown color that you observe here at the point at which you double the volume will be decreased. The brown coloration will be decreased, or the brown color's intensity of the brown color will be decreased. So one thing to note is, at this point the number of NO2 particles in each of these systems is still the same. One change that has happened over here is, since we have doubled the volume, concentration of NO2 has gotten halved. Over here we have a higher concentration of NO2, over here we have a lower concentration of NO2. But as time goes by, when we are establishing a new equilibrium, one thing that happens is, we know the reverse reaction is favored, so therefore little by little more and more nitrogen dioxide particles will be formed. Now the reverse reaction is going to be favored because, as we know, when we decrease the pressure of a system, according to Le Chatelier's principle, system will try to produce more and more gas particles to increase the pressure of the system. So therefore students, the reverse reaction produces more gas particles, so therefore reverse reaction is favored. And over here, now the concentration of nitrogen dioxide is going to be greater than the concentration of nitrogen dioxide here. And compared to the initial system, the number of moles of nitrogen dioxide in the final equilibrium is going to be greater than the number of moles of nitrogen dioxide in the initial equilibrium here. So that is something you need to keep in mind. Number of moles of nitrogen dioxide over here is greater than the number of moles of nitrogen dioxide over here. You might not see a darker color than this. However, keep in mind, if you compare the number of moles of nitrogen dioxide in each of these cases, over here the number of moles of nitrogen dioxide will be greater. The only reason why you don't see a darker color here is because a greater number of moles of nitrogen dioxide is now distributed in a larger volume compared to a somewhat small number of nitrogen dioxide being distributed in a very small volume. So these are the color changes you can observe when you are carrying out this experiment. Now students, at this point we have discussed all the theory parts that are important for the first part of this experiment. And in this particular experiment, experiment number 34, we have an additional experiment that we can conduct in the lab. So let's take a look at the theory parts that are associated with this additional experiment. Additional experiment, observation of the effect of temperature on the hexaquacobalt 2 complex and tetrachlorocobaltate 2 complex system. So we have an equilibrium system developed between these two complex ions. So we are going to observe the effect of temperature when we change the temperature of this equilibrium system. So we have this hexaquacobalt 2 complex reacting with chloride ions to turn into tetrachlorocobaltate 2 ions as well as 6 water molecules. So this hexaquacobalt 2 complex is pink in color. This cobalt complex is pink in color, and this tetrachlorocobaltate 2 complex ion is going to be dark blue in color. This complex ion is pink in color. This complex ion is dark blue in color. So when we add chloride ions to this hexa aqua cobalt 2 ion complex, you will see it will turn into a dark blue color tetrachlorocobaltate 2 ion complex. So if this equilibrium is present as an equilibrium mixture and you change the temperature, you are going to observe the reaction moving either forward or reaction moving in the reverse direction. So because of that, students, we will be observing color changes. The forward reaction for this particular equilibrium is going to be an endothermic reaction. We can see the forward reaction, the delta H, the enthalpy change, is greater than 0, indicating that the delta H value is a positive value. So the forward reaction is endothermic, the reverse reaction is exothermic. So let's take a look at what we are going to be doing here. Dissolve a small amount of solid cobalt 2 chloride sample in water. A pink color solution will be obtained. Yes, this particular complex ion is pink in color, so that is the first complex ion that is going to be formed. That is going to be pink color, so therefore the solution is going to be observed as a pink color solution. The complex formed here is given here, hexa aqua cobalt 2 complex. And when concentrated HCl is added to the solution, the color of the solution will turn to a blue color. The complex that is formed here is going to be COCl4 2 minus. So you can see, students, when you add concentrated HCl and increase the HCl concentration to a really high concentration, at that point the equilibrium will mainly be shifted towards the right hand side, producing more and more of this particular dark blue color copper chloride ion complex, tetrachlorocobaltate 2 complex. So it's a cobalt complex, not copper, a cobalt and chloride ion complex that is going to be dark blue in color will be formed. How do we prepare the equilibrium system? So to the above pink color solution we obtained by dissolving a small amount of cobalt 2 chloride. So to above pink color solution, we are gradually going to add HCl. So we can add HCl dropwise until it turns into a mix of the pink and the blue color. So we can say until it turns into a purple color solution. Or else we can start from this dark blue color solution and gradually add water until we obtain this purple color solution. So we can prepare this equilibrium mixture in two ways. We can start with the pink color solution and gradually add HCl until you obtain a purple color solution. Or you can start with the dark blue color solution and gradually add water and dilute the solution until you obtain a purple color solution. So in the pink color solution, the main complex ion that is going to be produced is this. In the dark blue color solution, the main complex ion that is going to be in the solution is this tetrachlorocobaltate 2 ion. But in the equilibrium mixture, you are going to have both of these ions. Due to the presence of both of these ions in more or less similar concentrations, you will observe both of these colors at once. So when both of these colors are mixed together, the color is going to be a purple color. So in this equilibrium system, you will observe a purple color. When the solution obtains this purple color, further addition of any reagent is stopped. So we are not going to add further. If you start from this end, we are not going to further add water. Or if you start from the pink color solution, we are not going to further add any HCl after obtaining this particular solution. Now we are moving on to the test that we can do, increasing the temperature. The purple color solution is separated into a few parts and one is kept as the control while the other is partially submerged in hot water. You can see we keep one as the control while partially submerging the other in hot water. So we know the forward reaction here is endothermic. The forward reaction is endothermic. So in hot water, according to the Le Chatelier's principle, what reaction is going to be favored? Is it the exothermic reaction or the endothermic reaction? The endothermic reaction is favored in a higher temperature. So when we increase the temperature of a system, the system will try to bring the temperature down by favoring the endothermic reaction. So energy absorbing reaction will be favored. When the temperature is increased, the heat absorbing endothermic reaction will be favored. Due to this, the forward reaction will be favored, and as a result, the solution will turn to a blue color. So students, since the forward reaction is favored, the concentration of tetrachlorocobaltate 2 ion concentration will actually increase, whereas the concentration of hexaquacobalt 2 ion will go down. So the pink color complex concentration will go down, and the dark blue color concentration complex concentration will go up. So due to that, the equilibrium mixture is now going to predominantly appear as a blue color solution, because this complex is blue in color, and that will be produced more as the equilibrium position shifts to the right hand side. So that is the observation when you add the equilibrium mixture into a hot water bath, or when you increase the temperature of this particular equilibrium system. Reducing the temperature. A portion of the purple color equilibrium system is placed on an ice bath, while the other is kept as the control. So we have this purple color mixture. We keep one aside as our control, while we place another in the ice bath. So ice bath will decrease the temperature of the system. So when the temperature of the system is externally decreased, what will the system do? System will try to increase the temperature by favoring or doing more of the exothermic reaction. If the forward reaction was endothermic, that means the reverse reaction is exothermic. So the reverse reaction or the backward reaction will happen more. So since the exothermic reaction is favored, the equilibrium position will shift to the left. That means a reverse reaction will be happening more, producing more and more of this pink color cobalt complex ion. So hexaquacobalt 2 complex ion will be formed more. So the concentration of that ion will increase, while the concentration of this tetrachlorocobaltate 2 ion concentration decreases. So this ion concentration goes down, while this ion concentration goes up. So students, because of that, the pink color in the solution will increase. Eventually, when the equilibrium is obtained, in the lower temperatures, you are going to observe that the equilibrium mixture appears mainly pink in color. When the temperature is decreased, according to Le Chatelier's principle, the heat releasing exothermic reaction will be favored. This means the reverse reaction is favored, and therefore the solution will turn to a pink color. We can very clearly observe that here. Now let's move on to the next part. Effect of ion concentration on equilibrium. So effect of Cl minus ion concentration. The purple color equilibrium solution is separated into few portions, and one is kept as the control. The other portions below reagents are added, and the color changes are observed. So first one, increasing the Cl minus ion concentration by adding HCl. So students, when you add HCl, the Cl minus ion concentration will increase. As you know, HCl is a strong acid, it dissociates fully in aqueous medium. So chloride ion concentration will be increased in the medium due to addition of HCl. So if Cl minus ion concentration increases, according to the Le Chatelier's principle, we will try to decrease the Cl minus ion concentration by carrying on the forward reaction. Then what happens? this particular complex concentration will increase, while the concentration of this complex will go down. So because of that, students, you will see the equilibrium mixture will turn to a blue color. So when you add HCl, that is the observation that you note here as well. So the purple color solution is now going to appear blue in color. As I mentioned here, this complex's concentration will increase when HCl is added to the medium. When Cl minus ion concentration is increased, the forward reaction will be favored. Forward reaction will be favored according to Le-Chatelier's principle. Therefore, solution will turn blue in color due to the equilibrium position shifting to the right. Due to the equilibrium position shifting to the right, we will have more and more of this particular complex formed, which will lead to formation of a dark blue color solution. Another way we can increase the Cl minus ion concentration is by adding a salt that contains Cl minus ions, like sodium chloride, or in this case we have added calcium chloride. So if you add calcium chloride, when calcium chloride 6H2O solid crystals are added, the Cl minus ion concentration in the medium will increase. Now students, don't get confused about this water of crystallization here. This is just few molecules of water attached to each crystal. So we are anyway conducting this experiment in aqueous medium. So just addition of this few molecules of water is not going to increase the concentration of water. However, when we add this particular solid, the chloride ion concentration will be significantly increased. Now, in a water sample, the concentration of water is anyway significantly high. So adding a few molecules of water like this is not going to make a significant change in the concentration of water. However, in this medium, the Cl minus concentration is somewhat moderate. At a point like that, if you add any salt containing Cl minus ions, there will be a significant increase in the Cl minus ion concentration. So when that happens, again, the same observations can be observed here. Cl minus ion concentration will increase according to Le-Chatelier's principle. The forward reaction will be favored. Equilibrium position will shift to the right, producing more and more of this complex that is blue in color. So therefore, the entire medium will turn to a blue color solution. So the Cl minus ion concentration in the medium will increase as the solid dissolves in the medium. When Cl minus ion concentration increased, the forward reaction will be favored according to the Le-Chatelier's principle. Therefore, solution will turn blue in color due to the equilibrium position shifting to the right. So when the equilibrium position shifts to the right, this particular complex that is blue in color will be produced more. Decreasing the Cl minus ion concentration by addition of silver nitrate. Now, as you know, students, silver nitrate readily reacts with chloride ions in aqueous medium. You will produce silver chloride. When silver nitrate is added to a medium that contains Cl minus ions, immediately silver ions along with chloride ions will produce silver chloride. Silver chloride is a water insoluble white color precipitate. So due to the formation of this precipitate, the chloride ion concentration in the medium will go down. According to Le-Chatelier's principle, we will try to produce more and more chloride ions because now the chloride ion concentration is reduced. So because of that, the reverse reaction will be favored. In attempts to increase the chloride ion concentration, when we do the reverse reaction more and more, the concentration of this hexaaqua cobalt 2 ion will go up. Concentration of this particular complex ion will go up, and this ion's color is pink in color. So therefore, when we reduce the concentration of Cl minus, the reverse reaction will be favored. Equilibrium position will be shifted to the left. Therefore, the concentration of this ion increases, producing a pink color solution. So you can see, students, in this diagram, a pink color solution is produced along with silver chloride. Now, silver chloride was produced because when we were trying to remove Cl minus ions, we remove the Cl minus ions by adding certain amount of silver nitrate. So silver ions and chloride ions will produce this white color silver chloride precipitate. When silver nitrate is added, the Cl ions in the medium will get precipitated as silver chloride. You can very clearly see the reaction here. It will produce a white color precipitate. Nitrate ions here will not interfere with the reaction that is taking place. However, silver ions will remove the chloride ions from the medium. So therefore, the chloride ion concentration will go down. Due to the formation of silver chloride precipitate, the chloride ion concentration in the solution will decrease. According to Le Chatelier's principle, the reaction that produces more chloride ions will be favored. This means the reverse reaction will be favored and the equilibrium position will shift to the left, which produces more of hex aqua cobalt 2 ion. This will turn the solution pink in color. So this complex ions concentration will increase and tetrachlorocobaltate 2 ion concentration will go down. So therefore, mainly a pink color in the medium will be observed. Now, what happens if you add water? What happens if you add water to this equilibrium mixture? So students, when you add water, the Cl minus ion concentration will decrease. Again, at that point also the reverse reaction is going to be more favored. When distilled water is added, the volume of the solution will increase, which will lead to decreasing the chloride ion concentration. Now, all of the ion concentrations will decrease, but here, over here, one of the products that are present here is water. So when it comes to the reverse reaction, water's concentration matters, but adding water is not necessarily going to make a huge impact in the concentration of water here. However, adding water will definitely affect the concentration of Cl minus ions. There's going to be a significant reduction in the concentration of Cl minus ions when water is added. So because of that, students, the equilibrium will shift to the left. The reverse reaction will be favored. According to Le Chatelier's principle, the reaction that produces Cl minus will be favored. So therefore, like I mentioned earlier, equilibrium position will shift to the left. So therefore, solution will be pink due to the producing or due to increasing the concentration of this complex, which happens to be pink in color. Right. What happens if we increase the cobalt ion concentration? Now we know when in this case, if you increase the cobalt ion concentration by adding CoCl2, 6H2O solid, you are going to observe the solution turning into a dark blue color. Let's observe why that is. When cobalt chloride 6H2O solid crystals are added to equilibrium system, cobalt 2 plus ion concentration will increase. Due to this, the concentration of hexaqua cobalt 2 ion will increase. So the concentration of this ion is going to now increase. So at that point, students, the forward reaction will be favored. As you know, when concentration of one particular ion increases, according to Le Chatelier's principle, the system will try to decrease that ion's concentration. In this case, when we increase the concentration of the hexaqua cobalt 2 ion, the forward reaction is going to be favored. So therefore, more and more of tetrachlorocobaltate ion will be formed. So that ion's concentration will go up. Due to that, the solution will turn to a dark blue color. This will cause the forward reaction to be favored according to Le Chatelier's principle. Therefore, solution will turn blue in color due to the equilibrium position shifting to the right hand side. So equilibrium position will shift to the right hand side, producing more and more of this particular ion, turning the solution into a dark blue color. So these are the observations that are associated with this particular equilibrium system. We have a few different observations here. So let's take a look at them. If you apply heat, now in all of these instances, before we started the experiment, the equilibrium system was purple in color. But when you apply heat, it turned to a dark blue color because the forward reaction was endothermic, so the forward reaction was favored. When you cool the system, since the reverse reaction was exothermic, reverse reaction was favored. So therefore, system turned into a pink color, producing more and more of this ion. Addition of solid cobalt chloride 6H2O. So when you add cobalt chloride into the medium, where it dissolves, it will mainly contribute to producing this hexaqua cobalt 2 ions. So hexaqua cobalt 2 ion concentration will go up in the medium initially. So when that happens, according to Le-Chatelier's principle, we will try to decrease that ion concentration by favoring the forward reaction. So this ion will be produced more as the reaction equilibrium position of the reaction shifts to the right. So therefore, a dark blue color solution can be observed. Addition of calcium chloride, addition of conc HCl. Both of these experiments that were done were aiming to increase the Cl minus ion concentration. So when Cl minus ion concentration is increased, students, the forward reaction will be favored to decrease the Cl minus ion concentration. So in attempts to decrease the Cl minus ion concentration, when the forward reaction is favored, the tetrachlorocobaltate ion concentration will increase. So because of that, the dark blue color will be the observation in the final equilibrium that is established. So the solutions will go from purple to dark blue color. When we add silver nitrate and distilled water, we saw silver nitrate will precipitate as silver chloride, right? Silver ions will remove chloride ions from the medium as silver chloride precipitate. And when you add distilled water, Cl minus ion concentration will be diluted. So therefore, Cl minus ion concentration will go down. So both of these instances, we are decreasing the Cl minus ion concentration. So when Cl minus ion concentration is decreased, the reverse reaction will be favored to increase the Cl minus ion concentration. So at that point, the hexaqua cobalt 2 ion concentration will increase. Therefore, the solution will turn into a pink color. So these are the observations associated with the test that we discussed in the previous slides. Important. Cobalt chloride 6H2O is a pink color crystalline solid. When the substance is dissolved in ethanol, the water in the solid sample will form hydrogen bonds with the ethanol molecules and will be removed from the solid. So from the solid, the water will be removed. This will lead to the formation of COCl4 which is blue in color. So we know COCl4 ion is a blue color ion, and when we add this cobalt chloride 6H2O into ethanol medium, due to the formation of hydrogen bonds between ethanol and water that is present in the solid, the water will be removed from the solid, producing a COCl4 ion. Due to this ion formation, the medium will appear blue in color. When water is added to the above system, the pink color will be observed. The system shows the Biller equilibrium. So after producing this blue color solution, if you add water to it, since now water is reintroduced into the medium, cobalt ions can form coordinate bonds with water ligands to form hexaqua cobalt complex, which is going to be a pink color complex, or pink color complex ion to be precise. So you can see over here, this tetrachlorocobaltate 2 ion is blue, hexaqua cobalt 2 ion is going to be a pink color ion. So if you observe over here, there are 4 chloride ligands forming coordinate bonds with cobalt 2 plus, and this particular complex ion that is formed is going to be blue in color, right? So the formation of that complex ion is indicated here. So now we observe the formation of the hexaqua cobalt 2 complex ion. So you can see over here there are 6 water ligands forming 6 coordinate bonds with the copper 2 plus ions to form this hexaqua cobalt 2 ion. Usually, students, you can write the complex like this and the charge outside of square brackets. You can indicate it this way as well. If a filter paper is soaked with aqueous cobalt chloride solution, the filter paper will also appear pink in color. Now we know in the aqueous cobalt chloride solution, we have the hexaqua cobalt 2 complex ion mainly producing this pink color. So if you soak a filter paper in such a solution, even the soaked filter paper is going to appear pink in color. However, upon heating, the water within the soaked filter paper evaporates, causing its color to transition to a blue color. So we can see when water is removed, the complex will turn into a blue color complex. The hexaqua cobalt complex will turn into a tetrachlorocobaltate 2 complex ion. So because of this, you will observe a blue color in the filter paper. The blue color filter paper prepared will be cut into small strips of filter paper as indicated below. You can very clearly see what we have done here. So we can use these cut pieces of blue color filter paper to identify the presence of water. So if water comes into contact with these filter paper that is blue in color now, it will turn back into a pink color. So we can use this filter papers that are soaked in a cobalt complex ion solution as another method to identify the presence of water. If you use a blue color filter paper strip like this that we prepared and introduce this into a bit of gas that is produced, or if you directly introduce into aqueous medium, due to the presence of water, this particular filter paper will turn into a pink color. As an example, if you take sodium thiosulfate 5H2O, this is the hydrated form of sodium thiosulfate, and if you heat it, the anhydrous sodium thiosulfate will be formed. Along with that, H2O gas will also be formed. Solid sample mentioned above is taken into a boiling tube and is heated thoroughly. While the heating is carried out, blue color filter paper strip that was prepared earlier is brought to the opening of the boiling tube. So when we bring this blue color filter paper strip that we prepared earlier, this is not a litmus paper, this is a blue color filter paper that we prepared, and when you bring it to this setup where we are heating sodium thiosulfate 5H2O, we know certain amount of water will be produced in the gaseous form. So water will come into contact with this filter paper, and as it comes into contact with the filter paper will now turn to a pink color. So the blue color filter paper will turn to a pink color. This can be used to identify the presence of water. So you can see the equation given here once more as well. So when the blue color complex is exposed to water, the blue color complex ion, when it is exposed to water, it turns into the hexaqua cobalt 2 complex ion, releasing chloride ions. So this hexaqua cobalt 2 complex ion is going to be pink in color, and that is why we observe a pink coloration here in the filter paper. Preparation of an equilibrium system. So apart from the equilibrium systems that we have looked at, there are other equilibrium systems that we can work with here as well. One equilibrium system that we can work with is the chromate and dichromate equilibrium system. So we can prepare the equilibrium system starting with an aqueous solution of potassium chromate, which is yellow in color. We can start with the potassium chromate solution, which is yellow in color. And when a few drops of sulfuric acid is added, that solution will change its color between yellow and orange. The solution formed at that point is our equilibrium system. So students, as you may know, the chromate ions solution is going to be yellow in color. A solution of dichromate ions is going to be orange in color. So chromate ion solutions are yellow in color, dichromate ions are orange in color. But if you start with a solution of chromate and gradually add H plus into the medium, the color of the solution will slightly change to a color between orange and yellow. So at that point we have prepared our equilibrium mixture. So as you can see here, we have a yellow color potassium chromate solution, but when we add dilute HCl drop by drop, we obtain a yellow-orange color solution. That means both the chromate as well as the dichromate ions are present here. Cr2O7 2 minus. So both the chromate and the dichromate ions are going to be present here. That is why we have this yellow-orange color. So over here we are repeating what we already know. We know the chromate ions are yellow in color and the dichromate ions are orange in color. However, when you're writing the equilibrium, we can write it in two main ways. We can write two chromate ions turn into one dichromate ion in the presence of 2 H plus, forming the dichromate ion and the water molecule. Apart from that, if you want to write the same equilibrium with the use of only 1 H plus, we can do so. So at that point, apart from the formation of the dichromate, you will only form a hydroxide ion. An equilibrium system can also be prepared with dichromate solution. So when a few drops of sodium hydroxide is added to an aqueous solution of potassium dichromate, a solution with a color that is in between yellow and orange can be formed. The solution formed at that point is an equilibrium system. So we know earlier we started with the chromate ion and obtained the equilibrium system. Here we are starting with the dichromate ion and get into the equilibrium system. So when you take the dichromate ion and if you add OH minus ions, as we saw earlier here, when you increase the OH minus ion concentration, the dichromate ions will get used up with OH minus and the reverse reaction will be favored. So therefore, small amount of chromate ions will also additionally be formed. So therefore, if you are starting with pure dichromate ion solution, when you add hydroxide, it will lead to producing chromate ions as well. So when both dichromate and chromate ions are present in the same mixture, we will observe both of their colors and we can say we have now prepared an equilibrium mixture. So if you take sulfuric acid and if you add excess sulfuric acid to our chromate ion solution, chromate ion solutions are yellow in color. If you add excess sulfuric, the equilibrium will be pushed further towards the right hand side, producing mainly our dichromate ions. So the equilibrium position will be shifted mainly towards the right, producing our dichromate ions. Because of that, the medium will mainly appear orange in color. So in the presence of excess H2SO4, the main product is going to be dichromate ions. Chromate ions will turn into dichromate. If you take dichromate and add excess sodium hydroxide, at that point, the reverse of this will happen. So dichromate in the presence of hydroxide ions will mainly turn into chromate ions. So orange color solution will turn into a yellow color solution. Now we are going to observe the effect of H plus concentration on the equilibrium. So when you add H plus, the yellow-orange solution with the dichromate equilibrium is taken into a few test tubes first, and then we will be increasing the H plus concentration of the equilibrium with the addition of sulfuric acid. So what will happen when you do that? We'll keep one as the control while we add sulfuric to the other. So when you keep one of the vials as a control, we can compare the original yellow-orange color that was present in the solution. But when you add sulfuric acid to this particular second test tube that contains the same solution, you will observe that solution's color will change to an orange color. So the equilibrium mixture that we have over here contains chromate as well as dichromate. However, in the presence of additional H2SO4, the equilibrium position will be shifted more towards the right hand side, producing more and more dichromate ions. So therefore, the solution turns into an orange color. So in the presence of higher concentrations of H plus, forward reaction le be favored according to the Le-Chatelier's principle, producing more and more of dichromate ions, which will make the solution orange in color. So as explained earlier, students, when H plus concentration increases, the forward reaction will be favored according to the Le-Chatelier's principle, which will lead to the increase of dichromate ions. So when dichromate ion concentration in the medium increases, the medium will appear orange in color. When dilute sulfuric acid is added to the solution, the H plus concentration will increase. Therefore, according to Le-Chatelier's principle, the forward reaction will be favored to remove the added H plus, leading to the formation of more and more dichromate ions, which will make the solution orange in color. Increasing OH minus concentration of the equilibrium solution. One of the test tubes containing the above equilibrium solution will be kept aside as the control. The other will be treated with dilute sodium hydroxide. So we can see, students, if you take this yellow-orange color equilibrium system and add dilute sodium hydroxide to one, it turns yellow in color. Now this is due to the formation of chromate ions. So as we increase the OH minus ion concentration, the reverse reaction rate will be increased, or we can say the reverse reaction will be favored according to our Le-Chatelier's principle. So because of that, the chromate ion concentration goes up, turning the equilibrium solution into a yellow color. When sodium hydroxide is added, this is another way of explaining what happens. When sodium hydroxide is added to the medium, H plus ions in the medium will react with the sodium hydroxide or hydroxide ions to form water. So yes, definitely, if there are H plus ions in the medium, H plus ion concentration will be brought down due to hydroxide ions reacting with the H plus ions in the medium. Due to this reaction, H plus concentration in the medium will go down. When the H plus concentration in the medium is decreased according to Le-Chatelier's principle, the reverse reaction will be favored to produce more H plus along with chromate ions. Due to the increase of chromate ions in the medium, the solution will appear yellow in color. So students, when we add OH minus ions to the medium, yes, OH minus ions will react with H plus ion concentration will come down when we additionally add sodium hydroxide into the medium. So because of that, the equilibrium will shift to the left, producing more and more of chromate ions, which happens to be yellow in color. So because of that, the entire solution will turn to a yellow color. With that, students, we can conclude the theory part that is revolving around experiment number 34. In the beginning of the experiment, we discussed how the factors like concentration, pressure, and temperature affect an equilibrium. We took nitrogen dioxide and dinitrogen tetroxide equilibrium in the first initial parts of this theory discussion. And after that, we looked at some other equilibriums as well. So by now, I hope you have developed a good understanding of the theory that is revolving around equilibrium systems. So with this, we can now move on to the lab and actually conduct this experiment and observe the observations that we need to make when you are carrying out this experiment. So let's move on out of this classroom and into the lab to actually conduct this experiment. GCE Advanced Level Chemistry Practical Series Experiment number 34, the experimental study of the effect of temperature on the gaseous system of NO2 and N2O4. The aim of this experiment is to develop a better understanding of the dynamic equilibria that exist in a gaseous system. Apart from that, we also aim to investigate the effect of applying some stress on the equilibrium position of a equilibrium system. So now, without further ado, let's move on to identifying the equipment and the reagents we will be using for this experiment. Now students, we have in front of us what we are going to be using for this experiment. We have nitric acid, we have copper turnings, as you can see. We have copper metal here, or copper turnings, and we'll be using this particular setup to react the copper turnings with nitric acid. So we are going to be using a thistle funnel that you have here to have more of a control over the addition of nitric acid to copper turnings. As nitric acid reacts with copper turnings or copper metal, you will see a brown color gas, nitrogen dioxide, will be formed. This setup will help us carefully deliver this nitrogen dioxide into each of these boiling tubes here. So let's identify what this setup contains. We have a conical flask here. We have a thistle funnel with a valve. We have a rubber stopper and a delivery tube connected to the rubber stopper to aid us in delivering the nitrogen dioxide gas into the boiling tubes. Apart from this setup, we'll be using a spatula, boiling tubes, and rubber stoppers to make sure whatever the nitrogen dioxide gas that we have taken into the boiling tube can be kept inside the boiling tube with the help of a rubber stopper. So we are going to be using the rubber stopper to seal the boiling tube. So these are going to be our chemicals and equipment we are going to be using for today's experiment. Now let's move on to the first part of our experiment. Students, we have in front of us the chemicals and the reagents we will be using for our experiment. We will be using concentrated nitric acid. We will be using copper metal. As you can see over here, we have copper metal in the form of copper turnings, small pieces of copper metal to increase the surface area of the copper metal that we are taking for this experiment. So these are small pieces of copper metal, also referred to as copper turnings. And then we have this setup where we have taken a conical flask, connected a rubber stopper to it, and we have a thistle funnel connected to the stopper for the easy delivery of nitric acid to copper turnings. So when we are conducting our experiment, we are going to take copper turnings and place it in the conical flask here, and then after closing the rubber stopper, we are going to be adding the nitric acid with the help of our thistle funnel so that we can carefully regulate the amount of nitric acid that is introduced into our copper turnings. So we have a valve here that will allow us to regulate the amount of nitric acid that gets introduced into this system. And then we have a delivery tube that will allow the gas that is formed inside this conical flask to be delivered into another container, such as the boiling tubes that we have here. Apart from this setup, we'll be using spatulas. We will be using a digital balance to measure about 5 grams of copper turnings. We'll be using a watch glass, boiling tubes, and rubber stoppers. These rubber stoppers will be used to seal the boiling tube and the gases within the boiling tube. Now, these are the equipment and the chemicals we will be using for our experiment. Let's move on to conducting the first part of our experiment. Students, in the first part of our experiment, we are going to be forming nitrogen dioxide gas. Nitrogen dioxide gas is an irritant gas, especially to the upper respiratory system. So, you should not be inhaling the nitrogen dioxide gas. Whenever you are conducting an experiment where you are producing irritant gases such as nitrogen dioxide, you should be conducting these experiments in a well-ventilated area or ideally inside a fume hood. So keep in mind, students, although we are conducting this experiment in a well-ventilated area right now, in the lab, you should be conducting these experiments in the fume hood. In this part of our experiment, we are going to be producing nitrogen dioxide gas by reacting copper turnings with nitric acid. We are going to measure 5 grams of copper turnings with the use of a digital balance that we have here, and we are going to be adding concentrated nitric acid to these copper turnings. When you add nitric acid to copper turnings, you can see a brown color gas is getting formed, and this brown color gas that is being formed in this system is going to be our nitrogen dioxide gas. So the formation of nitrogen dioxide gas is going to be very clear, as nitrogen dioxide has a very characteristic brown color in its gas. So you will be able to observe the formation of the gas due to the brown coloration of the gas that is being formed. When you add concentrated nitric acid to copper turnings, you can see the evolution of a brown color gas. The brown color gas that is getting produced here in this reaction is nitrogen dioxide. As the gas gets produced, we are going to use the delivery tube and deliver the gas that is produced into a boiling tube. After we have collected a certain amount of nitrogen dioxide into our boiling tube, we are going to close this boiling tube and seal the nitrogen dioxide gas inside our boiling tube. We are going to repeat that process 2 more times to obtain 3 boiling tubes filled with nitrogen dioxide gas. And as we are filling nitrogen dioxide gas into these boiling tubes, we are trying our best to obtain the same amount of color intensity inside each of these boiling tubes. So without further ado, let's move on to add nitric acid into copper turnings and produce nitrogen dioxide. For this, we have to use a digital balance. We are going to be turning on the digital balance. Afterwards, we can take a watch glass, place it on the digital balance, and then we can use the tare function of the digital balance to zero in the reading, and then we can move on to add copper turnings onto this wash glass with the use of a spatula. We are going to be taking around 5 grams of copper turnings. Now students, we have taken 5.06 grams. Since we need around 5 grams of copper turnings, this amount of copper turnings would do. So we are going to transfer this amount of copper turnings into our conical flask first. So let's go ahead and do that. Let's remove the rubber stopper from the setup that we showed earlier, and then let's carefully add our copper turnings to this conical flask we have here. Now students, as you can see, we have added our copper turnings into our conical flask. Let's move on to replacing the stopper over here, and then we can proceed to add nitric acid to the thistle funnel while making sure the valve over here is completely closed. Then after adding the nitric acid to our thistle funnel, we can slowly add our nitric acid little by little to our copper turnings to produce nitrogen dioxide gas. Let's move on to that step. Now let's take a concentrated nitric acid, and we can add a small amount of concentrated nitric acid into this thistle funnel that we have over here. Before we add it, we are going to make sure the valve is completely closed. Let's add a small volume of nitric acid into the thistle funnel. After adding a small amount of nitric acid, we will close the lid of the nitric acid reagent bottle and leave it aside. And now students, we have in this thistle funnel small amount of concentrated nitric acid. So when you're handling concentrated nitric acid, please be careful, as it is a very strong acid. You don't want this kind of strong acids to come into contact with your skin. So please do wear your personal protective equipment when you're handling strong acids such as nitric acid. Afterwards, we have our boiling tubes, and we have the rubber stoppers for the boiling tubes as well. We have removed the rubber stoppers and kept them ready. Friends, we have taken the nitric acid to our thistle funnel here. When we open the valve of the thistle funnel, nitric acid will be introduced onto the copper turnings that we have here. As it reacts with copper turnings, it will produce nitrogen dioxide gas. And this nitrogen dioxide gas that is produced is going to be delivered with the help of this delivery tube into each of these boiling tubes. We are going to introduce nitrogen dioxide gas that is produced into each of these boiling tubes. And after the boiling tubes are filled with nitrogen dioxide gas, we are going to remove the delivery tube and place a rubber stopper and seal the boiling tube along with the nitrogen dioxide gas that is present in it. And then we will be moving on to the next boiling tube. So we are going to fill 3 boiling tubes with nitrogen dioxide gas. So let's place the delivery tube in the first boiling tube and then move on to adding nitric acid. Now let's turn on this valve and allow the nitric acid to react with the copper turnings. You can see as nitric acid is added, a brown color gas is produced. This is nitrogen dioxide. Let's keep adding the acid. So the produced nitrogen dioxide gas is getting collected here. So as enough gas has gotten collected, we can move on to the next boiling tube. As you can see, students, we have collected this into 3 different boiling tubes. However, we can see they have different color intensities. So we will add a little bit more nitrogen dioxide to this boiling tube as well. And a little bit more to this as well. So now we have produced sufficient amount of nitrogen dioxide and collected into 3 different boiling tubes. Let's remove this setup from over here because it is producing more and more nitrogen dioxide, and as I mentioned earlier, it is not a gas that you should be inhaling a lot. So that is why we have sent it to a water bath here. As nitrogen dioxide is soluble in water, majority of the nitrogen dioxide gas that is bubbled through this water beaker will dissolve in the water, so we wouldn't get exposed to it as much. But we have collected nitrogen dioxide gas into 3 different boiling tubes here successfully. And as you can see, their color intensities are quite similar to one another. Let's remove this setup from the lab and move on to the next part of our experiment. Now, students, we have these 3 boiling tubes filled with nitrogen dioxide, and we do know about the equilibrium between nitrogen dioxide and nitrogen tetroxide. Nitrogen dioxide develops an equilibrium where a certain amount of nitrogen dioxide gets converted into dinitrogen tetroxide, and the forward reaction in this equilibrium is exothermic. Dinitrogen tetroxide is a more stable molecule compared to nitrogen dioxide. So when nitrogen dioxide turns into dinitrogen tetroxide, energy will be released. So therefore, we call the forward reaction to be a exothermic reaction. When dinitrogen tetroxide turns into nitrogen dioxide, that is an endothermic reaction. So in this equilibrium system that we have here, both of these forward reaction and the reverse reaction are happening at the same speed or the same rate. So the forward reaction rate and the reverse reaction rate in this equilibrium system is the same. Nitrogen dioxide is a brown color gas. Dinitrogen tetroxide is a colorless gas. So students, if the equilibrium position ever shifts either to the dinitrogen tetroxide side or more towards the nitrogen dioxide side, we can actually observe a color change. For example, if you increase the temperature of this system, the system will make use of the heat that is provided and carry out
the endothermic reaction more. Meaning, when you are increasing the system's temperature, the endothermic reverse reaction will be favored. Therefore, equilibrium position will shift more towards the left-hand side, producing more and more nitrogen dioxide gas, which is the brown color gas. So the brown color intensity inside this boiling tube is going to increase. If you place this boiling tube in a cold environment, a cold environment is a place where energy is lowered. So if energy is removed from this system, the system will try to oppose that and will try to produce more and more energy or release more and more energy. So in a cold environment, you will observe the exothermic reaction being favored. So the exothermic reaction in this equilibrium is the reaction where nitrogen dioxide turns into N2O4 or dinitrogen tetroxide, which is colorless gas. So when you place this boiling tube in a lower temperature, you can see the equilibrium position shifts towards the right hand side, producing more and more dinitrogen tetroxide due to favoring the forward reaction. So in a lower temperature, the forward reaction will be favored. In a higher temperature, the reverse reaction will be favored. So let's observe that in this setup. So to observe that, we are going to first place one boiling tube in water at room temperature, and we are going to take one boiling tube and place it in warm water or hot water, and we take the final boiling tube and we place it in cold water. In this case, we have a little bit of ice. We will add a little bit of water to this ice to make cold water. And you can observe how the color of each of these boiling tubes change. You can see that these boiling tubes have now three different colors. The boiling tube containing nitrogen dioxide that is placed in water at room temperature has not changed its color. The brown color that we observed initially when we filled the boiling tube with nitrogen dioxide can be observed here still. So we'll take it aside for the time being and we'll compare the boiling tubes that are placed in one in really hot water and the other in cold water. Do you see a color difference? The boiling tube that is placed in hot water now has a darker brown color, and the boiling tube that was placed in cold water containing nitrogen dioxide has a lighter brown color. We'll have to place them again in the system. So why is the equilibrium system that is placed in cold water has a lighter color, and why does the equilibrium system that is placed in warm water has a darker brown color? This is because when you place the equilibrium system in warm water or hot water, due to the high temperature in the hot water, the equilibrium system receives energy, and the reverse reaction, which is an endothermic reaction, will be favored. At higher temperatures or when you increase the temperature, the endothermic reaction is going to be favored. So therefore, equilibrium position will shift to the left. So the equilibrium we are talking about is the equilibrium where nitrogen dioxide turns into dinitrogen tetroxide. So on the left hand side, as a reactant, you have nitrogen dioxide. As a product, we have dinitrogen tetroxide. So the reverse reaction is endothermic. So when you place a equilibrium system in warm water, since the temperature is higher in warm water, the reverse reaction or the endothermic reaction that makes use of that additional heat will be favored, meaning the reverse reaction will be happening more to produce more and more nitrogen dioxide. So the equilibrium position shifts to the left. That is why we observe a darker brown color. That is because we have a higher concentration of nitrogen dioxide inside this equilibrium system. This equilibrium system also contains dinitrogen tetroxide, but in small amounts compared to the system that we have placed in cold water. So students, the darker color was observed due to producing more and more of nitrogen dioxide, which is a brown color gas. And when you're talking about the equilibrium system that was placed in cold water, it now has a lighter brown color. The lighter brown color is there due to nitrogen dioxide turning into dinitrogen tetroxide, which is a colorless gas. When the temperature is lowered, the exothermic reaction, which is the forward reaction, will be favored. In the beginning of this experiment, we mentioned nitrogen dioxide turning into dinitrogen tetroxide is an exothermic reaction. So at a lower temperature, the exothermic reaction will be favored. So when the exothermic reaction is favored, the colorless dinitrogen tetroxide gas will be produced more. Therefore, nitrogen dioxide concentration will go down and dinitrogen tetroxide concentration will go up. Because of that, the color intensity of the brown color that you see over here is low. Why? The concentration of nitrogen dioxide is less and concentration of dinitrogen tetroxide is higher. So students, equilibrium position has shifted towards the right hand side in cold water. So let's compare all three systems here. We have one equilibrium system placed in cold water, which has the lightest brown color. Another was placed in hot water, which has a very dark brown color. And in the middle, we have the equilibrium system placed in room temperature water. So you can see this was the original color that we observed when we filled dinitrogen tetroxide, when we filled nitrogen dioxide gas into the boiling tube earlier. It is slightly decreased the color because as the reaction obtains an equilibrium, some of the nitrogen dioxide gets converted into dinitrogen tetroxide. However, the color intensity is lowest in the equilibrium system that was placed in cold water. So students, before we conclude this experiment, let's compare the colors of the two equilibrium systems that were placed in hot water and in cold water. So on my left hand side, what I have here, what I am lifting up is the equilibrium system that was placed in hot water, and what I have here on the right hand side is the equilibrium system that I have placed in cold water. If we keep them out again, you will observe all three equilibrium systems again will return to the same color intensity. With that, let's move on to the next part of our experiment. Students, we come to you with a bit of an additional experiment where we have taken the nitrogen dioxide gas into a gas syringe. Now in this syringe you can see, due to the presence of NO2 gas, it is brown in color, but this is a closed system, so therefore we have the equilibrium where nitrogen dioxide exists with an equilibrium between nitrogen dioxide and dinitrogen tetroxide. So we do have both nitrogen dioxide here along with dinitrogen tetroxide. As you know, students, two nitrogen dioxide molecules will react to form one dinitrogen tetroxide. In the equilibrium, as the reactants, you have two nitrogen dioxide gas molecules, and the product would be one dinitrogen tetroxide. So in this equilibrium system, if you increase the pressure, what do you think would happen? As you know, the system will try to decrease the pressure by favoring the side which produces lower number of gas molecules. So in the left hand side of the reaction, or the reactant side of the reaction, we have two reactant molecules turning into one product molecule. Both of these are in gaseous phase. When I increase the pressure, the system would try to decrease the pressure. So when I push this syringe and increase the pressure inside the system would favor the reaction that would allow the system to decrease the pressure. Forward reaction reduces the number of gas molecules. When two nitrogen dioxide turns into one dinitrogen tetroxide, that reduces the number of gas molecules and therefore reduces the pressure. So the forward reaction where two nitrogen dioxides convert into dinitrogen tetroxide will be favored. However, the very first thing that you observe when I place it on the ground and pressurize this is, you can see, right, if I take this syringe and let's say I increase the pressure inside the syringe by pressurizing it, then what happens is, you can see the brown color increases immediately, but after a while you can see the brown coloration decreases little by little. So observe the color change again. You can see now the dark brown color turns to a lighter brown color little by little. Why is this happening? This is usually taking place when I increase the pressure. All of the gas molecules that were earlier spread in a larger volume is now spread in a much smaller volume. So it increases the concentration of both nitrogen dioxide and dinitrogen tetroxide. So when nitrogen dioxide is present in a smaller volume and has a higher concentration, we would observe a darker brown color. However, after a while, there will be an equilibrium that is established that favors the forward reaction, and therefore dinitrogen tetroxide will be produced more, which is going to be a colorless gas. Due to this, you will observe the color decreasing from dark brown to a little bit of a lighter brown. We'll observe that change again. Now when I release the pressure, you can see it becomes lighter brown. Now let's do it again and observe how the color changes. So let's press this down once more. You can see immediately the color changes to a dark color, but after a while it changes back little by little. As a new equilibrium is obtained, the color again will become a little lighter. Let's observe this one more time. Dark color immediately, and after that it will be decreasing little by little. We'll see again. When you apply pressure, immediately dark brown, and then gradually, very slowly, the dark brown color will decrease and form a lighter shade of brown. This is because as soon as I reduce the volume inside this syringe, the concentration of nitrogen dioxide will go up. So at higher concentrations, you will observe a darker brown color because nitrogen dioxide is brown in color. Higher concentrations will let us observe a darker brown color. However, since the high pressure favors the forward reaction of this equilibrium, more and more dinitrogen tetroxide will be formed. So therefore, the dark brown color will decrease gradually. So students, you will not be observing the dark color decreasing really fast, but it is going to decrease gradually. This is one of the exam questions that was asked some time back. What happens as soon as you decrease the volume in a system like this? So your answer should be, the first observation is you observe the brown color increase in its intensity, or we can see it turns dark brown initially, and afterwards gradually the color intensity of the brown color decreases and obtains a stable lighter brown color. So students, with that we can conclude today's experiment revolving around the equilibrium between nitrogen dioxide and dinitrogen tetroxide. We observed how the equilibrium system behaves when we change the temperature of the equilibrium system, and then with this syringe we observed how when we increase and decrease the pressure, how the equilibrium system changes its color, or how the equilibrium system behaves. After observing how the equilibrium systems behave when you change the temperature and pressure, we can now move on to another additional part of this experiment where we will be observing equilibrium that is seen in cobalt. So let's move on to that part of our experiment. Students, so as you saw, when we increase the pressure inside the syringe, we initially saw the color of the gas inside the syringe increased. It turned into a darker brown color, but it only lasted for a second. After that, it started turning again into a lighter brown color. Why is this happening? When you increase the pressure inside the system, the concentration of nitrogen dioxide initially increases. This is happening because when you increase the pressure, we increase the pressure by lowering the volume. So the number of nitrogen dioxide molecules that are spread in a larger volume will now be condensed into a very small volume, resulting in a high concentration of nitrogen dioxide, which will give us that initial darker brown color. However, when we keep applying the same pressure, we will observe in a new higher pressure, nitrogen dioxide will react to form dinitrogen tetroxide more. This is because when we increase the pressure of a system, the system will try to oppose that and will try to lower the pressure within the system. This could be done by favoring the reaction that produces a lower number of gas molecules. When two nitrogen dioxide molecules react to form one dinitrogen tetroxide molecule, you can see that particular type of reaction reduces the gas molecules. So therefore, the pressure within the system will decrease when favoring the forward reaction. So students, this is why when you keep applying a higher pressure, the color of the equilibrium system decreases. The dark brown color decreases to a light brown color because the new position of the equilibrium that is established is going to favor the forward reaction, where there is going to be more dinitrogen tetroxide produced, which actually results in a lower number of gas molecules within the system. So keep in mind, when you increase the pressure of a gaseous system, it will try their best to lower the number of gaseous molecules within that system by favoring the reaction that lowers the number of gaseous reactions that are being produced. Students, now we move on to an additional part of our experiment. So this experiment is going to be focusing on observing how the temperature affects the equilibrium position of an equilibrium system that is observed between hexa aqua cobalt 2 ions and tetrachloro cobaltate 2 ions. So let's move on to identifying the reagents we'll be using for this experiment. We have cobalt chloride to 6H2O, we have calcium chloride, we have ethanol, we have silver nitrate, concentrated hydrochloric acid. We'll be using spatula and we'll be using our test tubes to mix the reagents as well. So now let's move on to our first part of our experiment. Now let's take a small amount of cobalt chloride 6H2O. We have the hydrated cobalt chloride solid. Let's observe its appearance. It's a dark pink purple color solid that you observe here. Before we add any cobalt chloride into the beaker and make a solution with the use of ethanol, we are going to first measure a small amount of ethanol. So let's take our ethanol reagent bottle here and measure 25 milliliters of ethanol. Now students, we have measured 25 milliliters of ethanol into this measuring cylinder. Let's transfer that amount into a small beaker, like so. Let's take a small amount of cobalt chloride into a petri dish and observe the appearance of cobalt chloride. As you observe, cobalt chloride is a pink color solid. Now let's add a small amount of cobalt chloride into this ethanol solution we have here. Let's add a small amount of cobalt chloride into the ethanol that we have here. Now students, observe when we add cobalt chloride to ethanol, what you observe is the formation of a blue color mixture. Students, when we add cobalt chloride to ethanol, you can see the formation of a blue color solution. We can stir it a little bit with the use of a stirring rod. We are trying to obtain a dark blue color solution, so it will take some time. We'll continuously add more cobalt chloride. It will take some time for us to get to a blue color solution, dissolving all of the cobalt chloride here in the ethanol that we have here. We can observe the color. The blue color can be clearly observed here. right? I hope you can observe the blue color very clearly here. We'll mix it really well and we'll prepare a blue color solution of cobalt chloride. Now as you mix, you might observe the color changing to a pink color. This is because hexa aqua cobalt 2 ion is a pink color complex, and the solid that we introduced into ethanol had water molecules. So if you have enough water molecules in the medium, you will observe the formation of this pink color solution. Now students, we are starting to form a bit of a blue color solution, but if you are not satisfied with how dark the blue color is, you can add a little bit more cobalt chloride and continue to dissolve until a very clear blue color solution has been obtained. Now students, you can see we have formed a blue color solution here, and since we have dissolved this cobalt chloride 6H2O in ethanol, we have very small amount of water, but we have a lot of cobalt and chloride ions, resulting in formation of this blue color tetrachlorocobaltate 2 ion solution. So what you have here is a blue color cobalt chloride solution dissolved in ethanol. So in the first part of this additional experiment, what we did was we took small amount of cobalt chloride solid, cobalt chloride 6H2O solid, and we dissolved it in ethanol until we obtained a blue color solution. So you have to keep on adding more and more cobalt chloride 6H2O until you obtain a blue color solution. After preparing our blue color solution, we are going to take a few test tubes and separate the solution into a few test tubes. So let's separate it out into 5 separate test tubes first. Now we have taken this blue color cobalt chloride solution into 5 separate test tubes. For the first test tube, we are going to add a small amount of distilled water with the help of a dropper. We have distilled water here. We are going to add a few drops of distilled water to this test tube that we have here. So in this test tube we have cobalt chloride dissolved in ethanol. Now we are going to add water to it drop by drop. Observe the color change. Do you observe when it reacts with water, the solution starts to change its color, turning into a pink color. You can now very clearly see when you added water to this alcohol and cobalt chloride solution, we have formed a pink color solution here. So what is the reason for this pink color solution? Pink color solution over here is formed due to the presence of hexa aqua cobalt 2 plus complex ions. So hexa aqua cobalt 2 complex ions are going to have this pink color. When 6 water ligands form coordinate bonds with one cobalt 2 plus ion, you form hexa aqua cobalt 2 ions, which are going to have a pink color. The blue color that you observed earlier was due to the presence of tetrachlorocobaltate 2 ions. So this blue color complex is formed when 4 chloride ligands form dative covalent bonds with a cobalt 2 plus ion and form tetrachlorocobaltate 2 ion. So students, tetrachlorocobaltate 2 ion is going to be a blue color ion, and hexa aqua cobalt 2 ion is going to be a pink color ion. And there is an equilibrium that exists between these two ions. So let's take a look at the equilibrium first. Now you can observe here, when it comes to hexa aqua cobalt 2 ion, they are going to be pink in color, and tetrachlorocobaltate 2 ion is going to be blue in color. In the solution that we prepared by dissolving cobalt chloride in ethanol, we mainly had tetrachlorocobaltate 2 blue color ion. And as we added water, when we added more and more water, the equilibrium shifted, or equilibrium position actually shifted further to the left hand side of this equilibrium and started forming hexa aqua cobalt 2 ion, which is going to be pink in color. So when we added more water, the equilibrium shifted to the left. So students, this is a good example of how you can change the position of the equilibrium by adding either different amount of reactants or products. So we are going to keep adding water to 2 other test tubes containing this blue color solution that we have here. To that we are going to add more water. After adding a bit of water into this, we are going to now add a few drops of concentrated hydrochloric acid to the second test tube that we have here. So let's add a small amount of concentrated hydrochloric acid to this second test tube that we have here, and let's observe what type of color change can be seen when we add HCl to the second test tube here. we have concentrated HCl here. Let's add a few drops of concentrated HCl to this test tube and observe the color change. Can you observe, as soon as concentrated HCl is added to this pink color solution, the pink color solution is starting to turn blue. Can you observe that here? If you shake it, then you can see a clearer color change. We'll have to add a bit more HCl. You can see now the solution again turned to a blue color. Earlier on, it was pink in color. Afterwards, when we added HCl, it is now blue in color. So what happened? What happened to the solution and why is it now blue in color? Again, students, to explain this, we can bring in a document here. So if you observe this document, you can see this equilibrium is between these two cobalt complexes. And to the pink color complex, if you add a higher amount of HCl, or if you add a higher to the pink color complex, if you introduce a high concentration of Cl minus ions, then the equilibrium position will be shifted to the right hand side, producing more of this blue color complex, which is tetrachlorocobaltate 2 ion. So you can see when I introduced HCl or concentrated HCl into the solution, what we do is we introduce a higher concentration of Cl minus ions. As HCl dissociates in water, the Cl minus ion concentration in water will go up. So when I add concentrated HCl into the second test tube over here, the Cl minus ion concentration in that solution went up. So as the Cl minus ion concentration goes up, the forward reaction will be favored and results in forming this blue color complex more, which would lead to the observation that we had here, which is the formation of a blue color tetrachlorocobaltate 2 ion. So students, what happened over here is when we increased the concentration of one of the reactants, the equilibrium position shifted to the right hand side, producing tetrachlorocobaltate 2 ion, which is a blue color complex. And the reason for this blue color in our solution over here is the formation of tetrachlorocobaltate 2 ion. When we introduced a higher concentration of Cl minus ions into the medium, we can see the formation of tetrachlorocobaltate 2 complex, which is blue in color. As I mentioned, students, this blue color is there due to the formation of tetrachlorocobaltate 2 ion. So after making that observation, we can set it aside, and now we can move on to our third test tube. To our third test tube, we can add a little bit of calcium chloride. Students, before we add calcium chloride to this, ask yourself, what is the reason for this pink color? The reason for this pink color is the presence of this pink color complex, hexa-aqua-cobalt 2 ion. So hexa-aqua-cobalt 2 ion complex is present in this aqueous medium, and due to that we have this pink color observed in the solution over here. So what will happen when you add calcium chloride to this test tube? So before we observe the reaction. Let's take a look at what will take place. Calcium chloride is soluble in water. So if you take a little bit of solid calcium chloride and add it to an aqueous medium, the calcium chloride will dissociate to form calcium 2 plus ions and Cl minus aqueous ions. So when Cl minus aqueous ions come into this medium, the concentration of Cl minus aqueous ions are going to increase. So Cl minus aqueous ion concentration is going to rise, and as the Cl minus concentration rises, you would observe the color is going to change from pink to a blue color. As the Cl minus ion concentration rises, the forward reaction is going to be favored, resulting in tetrachlorocobaltate 2 ion. Now, let's move on to adding calcium chloride into our third test tube. We have our calcium chloride here. We'll take a small amount of solid calcium chloride and we'll add it to our pink color solution here. We have calcium chloride, which is a white color solid. We'll add few calcium chloride solid crystals into this solution that we have here. You can see there's a small blue coloration starting to appear at the bottom of the test tube. We mix it really well. You can see the blue color will increase. We will add a little bit more calcium chloride. We can observe a faster color change that way. You observe the color at the bottom has started to turn blue. At the top, it is still pink, but at the bottom, it is starting to turn blue. Why is this? When calcium chloride dissolves in water, due to the higher concentration of Cl minus ions that are going to be present in that region, tetrachlorocobaltate 2 complex ion will be formed, which is a blue color complex ion. So therefore, you can observe the bottom parts of this solution is going to be turning to a blue color, but still the top layers of this solution is pink in color. Since I haven't mixed this solution yet, the Cl minus ion concentration has not spread to the top layers over here, or in other words, I have not formed a homogeneous solution because I have not mixed this solution yet after the addition of calcium chloride. So if I mix it, you can see the blue color disappears as the Cl minus ions that were gathered over here spreads throughout the medium. If you allow all of the calcium chloride to dissolve, you will observe that this entire solution turns to a blue color. So let's observe the color change that gradually takes place as calcium chloride dissolves in this aqueous medium. As you continue to stir it or shake the solution, dissolving the calcium chloride, you can see the pink color starts to turn to a blue color. We can proceed to add a little bit more calcium chloride. As you can observe, students, when calcium chloride is dissolving in water, what can you see? The bottom part of this mixture is turning to a blue color. Again, as I explained earlier, this is due to the Cl- ion concentration increasing around these areas as calcium chloride dissociates and comes into the medium as Ca2 plus ions and Cl- ions. In this bottom part of our test tube or the solution, we will have a higher concentration of Cl- ions. Since I haven't mixed this mixture, the Cl- ions have still not moved on to the top layers. So we can still observe the pink color in the top layers, and we can observe the blue color in the bottom layers. Right? So if I mix it, when the Cl- ions get distributed throughout the aqueous medium, forming a homogeneous Cl- ion concentration, you will observe the blue color over here will disappear, and the pink color will start turning to a little bit of a darker color or moving towards a blue color. You can see when I mix it, pink color will gradually disappear and will start to turn to a blue color. So now you can see as calcium chloride dissolves in this solution, when more and more Cl- ions are introduced into the medium, Cl- ions concentration will go up. So therefore, the forward reaction will be favored and will produce tetrachlorocobaltate 2 blue color complex. So we started with this pink color complex. Now by this point, we can see the pink color complex we started with has now turned to a blue color. This clearly indicates in the presence of higher concentration of Cl-, the equilibrium position has shifted to the right hand side, producing the blue color tetrachlorocobaltate 2 ion complex. Now we have observed what happens when you increase the Cl- ion concentration in this equilibrium mixture. Let's move on to observe what happens if you decrease the Cl- ion concentration. When you increase the Cl- ion concentration, we saw the tetrachlorocobaltate 2 ion, which is a blue color ion, was formed. So what will happen if you remove Cl- ions from the medium? To remove Cl- ions from the medium, we can add silver nitrate. As you know, silver plus ions will react with Cl- ions to form silver chloride, which is a water-insoluble white color precipitate. So if you introduce silver nitrate into a blue color solution that we have over here, then what happens? The Cl- ion concentration will be coming down. So as the Cl- ion concentration comes down, you will start to observe the formation of a pink color solution. Now let's take our silver nitrate solution that we have here, and with the use of a dropper, let's add a few drops of silver nitrate to this blue color solution that we have here. Do you see, as I add silver nitrate, a white color precipitate is getting formed. Apart from that, you can see the formation of a pink color solution on the top layers as well. So we'll mix it really well, and let's add a generous amount of silver nitrate this time. You can see the formation of a white color precipitate along with a pink color solution. This is not a pink color precipitate that you form, students, you have to keep in mind. Now the observation is a bit more clear. So what you have made here is a suspension of silver chloride in a pink color solution. So silver chloride, as you already know, is a white color precipitate, water insoluble white color precipitate, and the aqueous medium has now turned to a pink color. The reason why it is pink in color is because we have formed hexa-aqua cobalt 2 ions. Hexa-aqua cobalt 2 complex ion is going to be a pink color complex ion. So due to the presence of hexa-aqua cobalt 2 ions, we observe this pink color in the aqueous medium. Right now it is a suspension with all the silver chloride solid particles suspended in the aqueous medium. But if you allow it to settle for a while, you will observe a white color precipitate collected at the bottom and a pink color aqueous medium as the supernatant. So we'll let it sit aside for a while, and we can actually move on to observe additional reaction here. That is, if you take a small amount of blue color solution, so if you take distilled water and add a little bit of distilled water to this, you observe the formation of a pink color solution. This is a hexa-aqua cobalt 2 ion complex, which is pink in color. If you take a small portion of it into a separate test tube and add HCl, you will observe the color changes to a blue color. We'll add a little bit more HCl. So as we added HCl, we have already observed the color of the pink color solution turns to a blue color. If you continuously dilute this solution, you will observe the blue color will disappear and will turn to a pink color. If you add more HCl, it will turn to a blue color. So this indicates we can shift the equilibrium of this particular equilibrium system by increasing the Cl minus ions or by increasing the Cl minus ion concentration or by decreasing the Cl minus ion concentration by adding more water. After conducting these experiments, we can now move on to a small summary of the first part of this additional experiment. When we initially prepared our solution dissolving cobalt chloride in ethanol, we had a dark blue color solution formed. When we added water to it, it turned to a pink color solution. Dark blue color solution is there due to the presence of tetrachlorocobaltate 2 ions, and the pink color solution is there due to the presence of hexa-aqua cobalt 2 ions. And when we added HCl to a pink color solution, we observed the formation of a blue color solution. This is due to HCl bringing in more Cl minus ions into the medium, increasing the Cl- ion concentration and favoring the reaction that produces tetrachlorocobaltate 2 ions. If you add more water to the solution, we saw it will again turn into a pink color solution. If you take our tetrachlorocobaltate blue solution and add silver nitrate, you will observe the formation of a pink color solution along with a white color precipitate. You can see here the white color precipitate is getting collected at the bottom. So when you add silver nitrate, to our blue color solution that we have over here, what happens is, students, silver nitrate would react with the Cl- ions in the aqueous medium and Cl- ion concentration will come down. As silver nitrate reacts with this equilibrium, the Cl- ions in the aqueous medium will come down. So as Cl- ions concentration go down, the equilibrium position will shift to the left hand, producing more and more cobalt hexa-aqua cobalt 2 plus ions, which are pink in color. So if you decrease the concentration of Cl- ions by adding silver nitrate and precipitating out the chloride ions, we decrease the concentration of chloride ions, then equilibrium will be shifted to the left hand side. When you add more Cl- ions, the concentration of Cl- will go up. Therefore, the forward reaction will be favored, producing the blue color tetrachlorocobaltate 2 ions. So when you add calcium chloride into the mixture, we also observed the Cl- ion concentration goes up. Therefore, the forward reaction is going to be favored, producing more and more tetrachlorocobaltate 2 ions, which are blue color complex ions. So therefore, when you added calcium chloride also, we observed the solution is turning to a blue color. Now, this is a quick summary of the first part of this additional experiment. Now, let's move on to the second part, where we are going to be subjecting this equilibrium mixture to two different temperatures, and we are going to observe how the colors change when we subject this equilibrium system to a hot and a cold temperature with the use of a water bath and an ice bath. Now, students, we have our blue color solution that we prepared earlier. Let's take that solution into a boiling tube. And we can move on to adding some distilled water until we can observe a purple color. A purple color will be observed when there is both the pink color complex and the blue color complex present in more or less equal concentrations. So when you have hexa-aqua cobalt 2 ions, which are pink in color, and tetrachlorocobaltate 2 ions, which are blue in color, in more or less equal concentrations, you are going to observe a purple color here. At that point, we'll stop adding water, and then we are going to place that particular equilibrium mixture in two different temperatures. We have a beaker filled with ice water, and we have a beaker filled with hot water here. So we are going to be placing these two equilibrium mixtures in these two beakers. So let's add water little by little until we observe a purple color. Let's add a little bit more of our solution because this is closer to pink than purple. So let's add a little bit of our solution. දම් පාටක් වගේ එකක් කියන්න. Now after adding a little bit of water, and then if you add too much water, you can again add a bit more of the solution that you initially prepared. We have gotten to a bit of a purple color equilibrium mixture here. We are going to take a few test tubes and separate this equilibrium mixture out. You can see very clearly when it's being poured down, you can see it's a purple color solution. We are going to separate it out into 3 test tubes. Students, we have now separated this purple color equilibrium mixture into 3 separate test tubes. We are going to keep one as our control. We are not going to change the temperature of the control that we have here, but we are going to take the other 2 test tubes and we are going to place one in cold water and the other in hot water. And we are going to observe how these 2 reaction mixtures or equilibrium mixtures are going to change their color when they are placed in cold water and in hot water. Students, now let's observe what has happened when we allow these equilibrium mixtures to reach a new equilibrium at their new temperatures. In cold water, the sample we placed has now turned to a pink color. If you compare it against the control, you can see the control was a purple color, but the equilibrium mixture that we have over here is now a pink color. This is because we have hexa aqua cobalt 2 ions formed with a high concentration over here in this equilibrium mixture, giving this solution a pink color. And in the second equilibrium mixture that we have over here, we observe a blue color or color more towards blue. This is because the concentration of tetrachlorocobaltate complex ion is higher in this particular solution. So the equilibrium has shifted to produce more and more tetrachlorocobaltate 2 ions, which is going to be a blue color ion. So therefore you observe a blue color here. If we compare the original sample that we started this with, all 3 samples had this purple color, but after we placed them in different temperatures, we observe that colors of these equilibrium mixtures changed based on the temperature they were subjected to. So what is taking place here? Let's observe what actually takes place with the use of our equation. Now students, we initially when we started this particular reaction, we made sure the color was purple. That is because we had somewhat equal concentrations of the blue color tetrachlorocobaltate 2 complex and pink color hexa aqua cobalt 2 complex. So when we had equal quantities of or equal concentrations of these 2 ions, we had a purple color. But when we place this equilibrium mixture In cold water, we observed the solution turned pink, meaning in cold water, hexaquacobalt 2 complex was formed with a higher concentration, indicating the reverse reaction was favored. So when we decrease the temperature of the system, in order to resist that change, according to Le Chatelier's principle, there will be action taken by the system. In this case, when you decrease the temperature, system will try to increase its temperature by carrying out the exothermic reaction more. So therefore, the reverse reaction has happened more here, indicating the reverse reaction is exothermic. So when we place this reaction mixture in cold water, the reverse reaction has happened more, so that when the reverse reaction is happening, more and more energy is released while producing this pink color complex. At lower temperatures, exothermic reaction is going to be favored, and as the exothermic reaction is favored, equilibrium position will shift to the left hand side, and as the equilibrium position shifts to the left hand side, you can see higher concentrations of hexaquacobalt 2 ions, which are pink in color. When we place the equilibrium mixture in hot water, we observed a blue color. This is because as we provide more heat to the equilibrium mixture, equilibrium position has shifted to the right hand side, meaning the forward reaction was endothermic. The provided heat was used to carry out the endothermic reaction more and was favoring the endothermic reaction, producing more and more tetrachlorocobaltate 2 complex ion, which is a blue color ion. So in hot water, we can see the equilibrium position shifts to the right hand side. Equilibrium position shifts to the right hand side, producing more and more of this blue color complex. I hope this particular example was very clear to you, students. With that, we can conclude this additional part of experiment 34. Theory parts revolving around this experiment and other questions revolving around experiment 34 will be discussed in our next session. Let's move on to the studio.
Welcome back to the classroom, students. So in the first session revolving around experiment number 34, we learned about the theory parts, and then we went into the lab and actually conducted the experiment. And here we are. Now we are going to be doing some questions that are associated with the experiment number 34. So let's take a look at the first question that we have here. At temperatures above 350 Kelvin, gas A undergoes a reversible reaction to produce gas B and gas C. 2 moles of gas A and 1 mole of gas B and 1 mole of gas C is added to a vacuumed container that has a volume of 4.157 cubic decimeters and was heated to 500 degrees Celsius. 500 Kelvin is well above 350 Kelvin. So that means the equilibrium that this question stated earlier can be observed at this temperature. When the system reached an equilibrium at this temperature, 1.6 moles of A, 1.2 moles of B and 1.6 moles of C was observed. So these are our equilibrium number of moles of A, B and C gas. Write the balanced chemical equation for the decomposition of A producing B and C. Write an expression for the equilibrium constant Kc for this reaction and calculate Kp. Keep in mind, don't get mistaken, we are asked to write an expression for Kc, but then we are asked for the value of Kp. calculate the Kp value of the reaction at 500 Kelvin temperature. If the Kp value in SI units is 5.1 into 10 to the power 13 at 700 Kelvin temperature, determine whether the decomposition of a gas is exothermic or endothermic. So we have to figure out whether the forward reaction is exothermic or endothermic. So let's move to answer the first question. Write the balanced chemical equation here. So we know that A is undergoing a decomposition to produce gas B and C. We are given the initial number of moles, so we'll write that down. Initial number of moles, we can write it down here. Initial number of moles. Initial number of moles. So we started with 2 moles of gas A. So the initial number of moles is given in moles, and as 1 mole of B, 1 mole of C. 1.0 moles of B, 2.0 moles of A was given. And we can write at equilibrium. We need to figure out at equilibrium the number of moles. Again, we are given this piece of information. They say at equilibrium at 500 Kelvin temperature, when the equilibrium is established, we found that there were 1.6 moles of A, 1.6 moles of A, 1.2 moles of B, and 1.6 moles of C. So we already had initial number of moles of B and C, don't forget. And these are the number of moles of each of the products and the reactant that we find at equilibrium. So then, if that is the case, we can find out the actual number of moles that reacted and the number of moles of the products that got produced. So I can write here reacted as well as produced number of moles. Produced moles. Reacted / produced number of moles. So we know if we initially started with 2.0 moles and now we are left with 1.6 moles, the number of moles that actually reacted was 0.4 moles, is it not? Right? So this is the difference will give us the number of moles of A that actually got reacted, 0.4 moles. And when you talk about B, we can see we initially started with 1.0 moles, but now we are left with 1.2 moles. That means 0.2 moles have gotten produced, because we anyway in the initial stage introduced 1 mole, but at equilibrium we have 1.2 moles, meaning there's a difference of 0.2 moles. Now additional 0.2 moles are here now, meaning 0.2 moles have gotten produced through this reaction. Over here also we can see initially we only introduced 1 mole. Right now we have 1.6, that means 0.6 millimoles have gotten produced. So these are the number of moles that reacted of A, and these are the number of moles that got produced of B and C. So we can now move into observing the molar ratios. Simplest molar ratio would be over here. If you divide all of them by the smallest number, which is 0.2 here, answer would be 2, 1 and 3. So this is the ratio in which they reacted. So that would indicate these are their stoichiometric coefficients. So when two molecules of A react, one molecule of B and three molecules of C should get produced, because we obtain this ratio by the analysis of equilibrium number of moles and the initial number of moles we introduced into the system. So at that point we can write this reaction. We know it's an equilibrium reaction, so we can include reversible arrows like this. So we have 2A reacting to produce 1B and 3C. So this happens to be our balanced equation for this equilibrium reaction. 2A, 1B, 2A will produce 1B and 3C. So the answer for this question is that. We can write the values here as well now, since we know the answer. 2A will react with will react to produce 1B and 3C. So if you want, you can indicate 1 here, but usually we don't write the 1 in front of a reactant or a product. But if it is any other number than 1, we will include that. So this is the balanced chemical equation for the reaction that is given in this question. Write an expression for the equilibrium constant Kc for this reaction. So we can now move on to write the expression for equilibrium constant Kc. So we know 2A gas forms 1B and 3C. So because of that, we can write the Kc equation the following way. Kc is equal to product concentrations raised to their stoichiometric coefficient as powers. So we can write product concentration raised to the power of their stoichiometric coefficient. So B gas concentration raised to the power of 1. So we don't have to include the power 1 here. And we have concentration of C gas raised to its stoichiometric coefficient. Over here, the power would be the stoichiometric coefficient that you see in front of C, which is 3. So concentration is going to be raised to the power of its stoichiometric coefficient. And when it comes to A also, we have number 2 in front of it, so that will be the power of concentration of A. So at that point, we have now written the Kc expression for this given equilibrium. Write an expression for the equilibrium constant Kc for the reaction. So this is going to be the expression for our given equilibrium. Now we can move on to the next part. Calculate the Kp value for the reaction at 500 Kelvin temperature. For the reaction at 500 Kelvin temperature. So students, over here we are given with some details that we can use to find out the overall pressure of the system. And after that, with the use of the partial pressure, we can find out the partial pressure, or with the use of Dalton's partial pressure equations, we can find out the partial pressures of A, B and C. And after that, we can use the Kp equation or expression for Kp to find out the Kp value. So over here, we are starting with the number of moles of A, B and C. And apart from that, we are given the overall volume of the container. Since in the beginning we have vacuumed this container, we know there are no other gases, only these gases are present in the container. So the total pressure of the container will be coming from these gas molecules at that temperature, 500 Kelvin temperature, and the volume of the container is 4.157. So let's find out the total number of moles. 1.6 plus 1.2 plus 1.6. So we can write the total number of moles in total is equal to total number of moles of A plus number of moles of B plus the number of moles of C. There was 1.6 moles remaining in A, 1.2 moles present in B, and 1.6 moles present in C. So when you add all of them together, it will be 4.0 mole. 4.0, actually it will be 4.4 moles. 4.4 moles, not 4.0, 4.4 moles. So now we have found number of moles of that is present, number of moles that is present at equilibrium in the container. And the volume of the container was given as 4.157 cubic decimeters. We'll double check that value. Volume was 4.157 cubic decimeters, and the temperature was 500 Kelvin. Now we can convert decimeters cube volume into meters cube without any issue. We know how to convert that. We can divide this by 1000, or we can multiply it by 10 to the power. We can multiply it by 10 to the power minus 3. So at that point, we will have the value of the volume of the container in meters cube, and we will need the volume in meters cube when we're using the ideal gas equation. So now we can use this PV equals nRT equation to find out the pressure, total pressure of the system. Total pressure of the system is equal to nRT divided by volume. So number of moles over here is going to be 4.4 moles multiplied by 8.314 joules per Kelvin per mole and over here the temperature is 500 Kelvin. And the volume is 4.157 into 10 to the power minus 3 meters cube. So you can see when you are trying to solve this that 4.157 and 8.314, they have a relationship. You can see 8.314 is twice as much as 4.157. So we'll have a 2 over here. So 2 multiplied by 500 is 1000. And plus you can see 10 to the power minus 3. When you bring it above the line, it will be 1000 as well. So that means the answer over here is going to be 4.4 into 10 to the power 6 pascals or newtons per meter. You can write the answer in pascals or newtons per meter. Both will be correct. We can write it as newtons per meter square, newtons per meter square. 4.4 into 10 to the power 6 newtons per meter square. Not newtons per meter, newtons per meter square is the correct unit. So students, now we have found out the total pressure of the system, but they are not asking for the total pressure of the system. They are asking for the Kp value, meaning we would have to calculate the partial pressure of each of the gases. And before we do that, we have to know how to use this total pressure, this is our total pressure, to calculate the partial pressure of each of the gases. And we know partial pressure of a gas is equal to the total pressure multiplied by the mole fraction. So when it comes to, let's say, partial pressure of gas A, partial pressure of gas A is going to be equal to the total pressure, let's say PT, multiplied by mole fraction of gas A. Now partial pressure of gas A can be found this way. So we know the total pressure is 4.4 into 10 to the power 6, and mole fraction would be, we know there is 1.6 moles of A. The total number of moles would be 4.4 moles. So number of units over here, moles cancel off, and only the pressure units, Newton per meter square, will be there. So you can see 4.4 cancels off the 4.4 here. So the final answer will come as 1.6 into 10 to the power 6 Newton per meter square. Newton per meter square. So this is the partial pressure of gas A. Partial pressure of gas B would be found the same way. Pb is equal to Pt multiplied by the mole fraction of B. So we have 4.4 into 10 to the power 6 multiplied by mole fraction of B would be 1.2 over 4.4, right? So the unit over here cancels off, only unit is going to be this that is going to be present. So 4.4 cancels off, giving us 1.2 into 10 to the power 6 Nm minus 2. Now, in a similar way, we can find out Pc as well. As you know, since we'll be following the same way, we'll directly use the equation 4.4 multiplied by, this is the total pressure, multiplied by the mole fraction. So it is 1.6 divided by 4.4. At that point, the answer would be the same as the answer that we see for partial pressure of gas A, because the number of molecules or number of moles of C and A happens to be the same. So the answer would be 1.6 into 10 to the power 6 Na minus 2. So this is the answer for the partial pressure of C. Now we have found out the partial pressure of all the gases. So now it is time for us to write an expression for Kp. Kp is equal to the partial pressure of each of the products raised to the power of their stoichiometric coefficient. So we have partial pressure of gas B multiplied by partial pressure of gas C to the power 3 divided by partial pressure of gas A to the power 2. So when we write the answer, we can see our partial pressure of B is going to be 1.2 into 10 to the power 6 multiplied by, over here we have 1.6 into 10 to the power 6 to the power 2, power 3 actually, divided by 1.6, because A's partial pressure was also 1.6, multiplied by 10 to the power 6 to the power 2. Now, when you carry out this calculation, you will observe that we have similar values here. This is 1.6 to 10 to the power 6 multiplied by itself. So this whole term to the power 2, and the same term is present here to the power 3. So they will cancel off, leaving only one of these 1.6 into 10 to the power 6 terms behind. So only this one term will be left behind. So when you carry out this calculation, if you multiply 1.6 by 12, 1.6 by 1.2, you will find the value is going to be here 32 and 16. So the answer is going to be 1.92. 1.92. 2 multiplied by 16, 32. And then we have 16 here. And therefore, answer is going to be 1.92. So we can write the answer is 1.92. And then there are two 10 to the power figures. So the 10 to the power figures, since the base is the same, the powers will be added. It will be 10 to the power 12. It will be 10 to the power 12. And the unit will be, each of these places have nm to the power minus 2, nm to the power minus 2. So since there are two of them, the unit is going to be n to the power 2, m to the power minus 4. N to the power 2, m to the power minus 4. So this is the Kp value. This is the Kp value of this question. This is the Kp value of this equation. So the answer to this question is going to be 1.92 into 10 to the power 12 n to the power 2 m to the power minus 4. Let's move on to the next question. If the Kpu value in SI units is 5.1 into 10 to the power 13 at 700 Kelvin temperature, determine whether the decomposition of A is exothermic or endothermic. So at 700 Kelvin, right, we write this reaction at 700 Kelvin. The Kp value was 5.1 into 10 to the power 13. In SI units, that means n to the power 2 m minus 4. But we have already found out the Kp value at 500 Kelvin. 500 Kelvin, the Kp value was 1.92 into 10 to the power 12. To the power 12 and to the power 2 m minus 4. So you can see that if you compare these values, the above value is actually much higher. So let's convert both of them into the same 10 to the power figure. So that means this will be 51.0 into 10 to the power 12 nm minus 2. Or actually nm, or n to the power 2 minus 4. N to the power 2, m to the power minus 4. So now students, when you compare these two values, we can very clearly see that the Kp value for the equilibrium that is obtained at 700 Kelvin is much higher than the Kp value for the equilibrium at 500 Kelvin. So that means when we were carrying out this reaction where 2A gas, this is the equation, 2A gas turns into 1B gas and 3C gas. This was the equation. And the Kp expression would be partial pressure of B multiplied by partial pressure of C to the power 3 divided by partial pressure of A to the power 2. So for the Kp value to increase, the values on the numerator, the Pb and Pc values should increase. And if that means if these two partial pressures are increasing, obviously the partial pressure of A is decreasing. That means, students, in order for that to happen, the forward reaction has to happen more, right? So at that point only we will see partial pressure of B and partial pressure of C will increase because the mole fraction of B and mole fraction of C has increased, indicating the forward reaction was favored. We can say the forward reaction is getting favored at a higher temperature compared to the 500 Kelvin. At 700 Kelvin, we can see that the Kp value is much higher, indicating that the equilibrium position was shifted to the right hand side due to favoring the forward reaction. So when the temperature is increased, we know when the temperature is increased, the endothermic reaction will be favored. Endothermic reaction will be the reaction that is going to be favored. So that means when we increase the temperature to 700 Kelvin, the forward reaction has been favored, meaning the forward reaction is the endothermic reaction. So students, they're asking us in this question, determine whether the decomposition of A is exothermic or endothermic. So very clearly, decomposition of A is endothermic. The answer is decomposition of A is endothermic, but you will have to construct your answer and properly write the answer. You can actually write the answer in the following manner. You can show that at higher temperature, the Kp value is much larger than at lower temperature, which is at 500 Kelvin, the Kp value is much smaller, but 700 Kelvin Kp value is much higher. That means at higher temperature, according to this equilibrium, the forward reaction was favored. That is why the Kp value is having a greater numerical value. So for Kp value to have a greater numerical value, we have to say that the partial pressure of B and partial pressure of C has increased. Now, how is that happening? The forward reaction should happen more, producing more and more of B and C products. So you can mention first, the Kp value at higher temperatures is much greater than the Kp value at the lower temperature, meaning at the higher temperature, according to the equilibrium expression, according to the equation, we can say at higher temperature, the product concentration or product partial pressures have been greater, meaning the forward reaction was favored when the temperature was increased. Because of that, we can determine that the forward reaction is endothermic. As we know, according to Le-Chatelier's principle, when we increase the temperature, the endothermic reaction will be the reaction that is favored. So students, that is how you will be structuring your answer. You have to mention the Kp values being different. You have to mention what the increase of Kp value would mean and how that increase is brought about. What reaction needs to happen more in order to bring about that change. So increase the temperature led to that particular change or that particular reaction happening more, indicating that reaction was the endothermic one. Right? So when you're writing your answer, you have to structure your answer in that particular manner. So just to repeat what we learned here, at 700 Kelvin, the Kp value will be much higher compared to 500 Kelvin Kp value. That indicates, according to this equation and the equilibrium Kp expression, that the product concentrations were higher compared to reaction concentrations. So product concentrations being higher at a higher temperature means the forward reaction was favored. If the forward reaction was favored when the temperature was increased, that indicates that the forward reaction is the endothermic reaction, and the reverse reaction would be our exothermic reaction. So decomposition of A is a endothermic process. The Kp value at 700 Kelvin is greater than the Kp value at 500 Kelvin. This means the partial pressures of B and C has increased when the temperature was increased. Therefore, it can be concluded that the forward reaction was favored when the temperature was increased. And the final bits will write in different color for clarity. According to Le Chatelier's principle, when the temperature is increased, the endothermic reaction favored Therefore, we saw that in this answer we have said earlier, forward reaction was favored, and now according to Le Chatelier's principle, we clarify the fact that the reaction that is favored is going to be the endothermic reaction. So we can say, therefore, the forward reaction is the endothermic reaction. So of the above equilibrium, the forward reaction is the endothermic reaction. Now students, with that, we can move to the next question. But if you want to have a look at the overall answer is given here. Now, the first part of the second question asks us to write down the Le Chatelier's principle. And then describe the shift in equilibrium predicted by Le Chatelier's principle when the temperature is raised in the following equilibrium systems. Additionally, explain the impact of increasing the pressure on the equilibrium as well. So we have to actually mention what happens when we increase the pressure as well as the temperature of each of these systems. So we'll talk about it in the second part of this second question. So the first part of this question asks us to write the Le Chatelier's principle. You can write Le Chatelier's principle states if a system at equilibrium is subjected to a change of temperature, pressure, or concentration of reactants or products the system will adjust to counteract the change and establish a new equilibrium. Establish a new equilibrium. Now, students, this is what Le Chatelier's principle states. So, we can now move on to the next question. So, what type of equilibrium shifts will happen if we increase the temperature when the temperature is raised or increased in each of these equilibriums, in each of these equilibriums. So first of all, we can see over here in the first reaction, it is a heat releasing reaction, meaning this is the forward reaction is going to be an exothermic reaction because it is a heat releasing reaction. That means the forward reaction is going to be having a negative enthalpy value. And the second reaction is a heat absorbing reaction. That means the delta H is going to be a positive value, meaning an endothermic reaction. So we know when it comes to the first part of this question, increase in temperature, the first equilibrium, we'll call it equilibrium A. If you take a look at this particular equilibrium, we can say based on the enthalpy value or information that we have been provided about the enthalpy, we know the forward reaction is exothermic. So when we increase the temperature, according to Le-Chatelier's principle, the endothermic reaction will be favored. Endothermic reaction is the reverse reaction. So we can say the reverse reaction will be favored. Again, according to Le-Chatelier's principle, according to Le-Chatelier's principle, endothermic reaction, in this case reverse reaction, will be favored. So according to what happens here, due to increase in the temperature, according to the Le-Chatelier's principle, the reverse reaction is going to be favored, as the reverse reaction is the endothermic reaction. Whenever we increase the temperature, the reverse reaction in this case will be favored, as the reverse reaction is the endothermic one. So in this particular experiment, or in this particular reaction, it is the reverse reaction that is endothermic, right? So it doesn't matter whether the forward reaction is endothermic or the reverse reaction is endothermic. When you increase the temperature, the endothermic reaction is going to be the reaction that is favored. So in this case, since the reverse reaction is the endothermic reaction, the reverse reaction will be favored. So if you take a look at the next reaction, reaction number B, we have X2Y4 turning into X2Y4 gas turning into 2XY2 gas. Now we know that this particular reaction has an enthalpy value that is going to be positive. We can say enthalpy value is greater than 0. That means forward reaction is endothermic. Earlier on, the reverse reaction of the previous equation was endothermic. Here, the forward reaction is very clearly endothermic. So we can say, now since we have given you the way in which you should answer, you can directly write here, when the temperature of the system is increased, according to Le-Chatelier's principle, the endothermic reaction will be favored. So therefore, since the forward reaction here is endothermic, forward reaction will be favored. And we need to include one additional detail even in the previous answer. We can write here in the previous answer, due to this, therefore, equilibrium position shifts to the left. Shifts to the left. But when it comes to the second reaction, the forward reaction, is endothermic. So therefore, the forward reaction will be favored. Reaction will be favored. When the temperature is increased. As the forward reaction is endothermic. You have to mention according to Le Chatelier's principle, but I'm just over here giving you the basic write-up. So we can write, therefore, the equilibrium position shifts to the right. Equilibrium position will shift to the right when the forward reaction is favored. Right, students. So apart from that, now we can also discuss what happens over here. So I will give you the answers to the second part of this question. What will happen when the pressure is increased? So for the first equilibrium, we can say on both sides, if you observe here, on both sides, we have only two gaseous moles present. The other reactant over here is a solid, so it does not contribute to increasing or decreasing the pressure of the container. However, when the reaction is proceeding forward or in the reverse direction, the number of gas molecules that are produced are the same. So when we increase the pressure of the system, when it comes to the first equilibrium, there is no specific direction that the equilibrium will be shifting to, because as we know, according to Le Chatelier's principle, when we increase the pressure of a gaseous system, according to the Le Chatelier's principle, the gaseous system will favor the reaction that produces a lower number of gas molecules. Right? So over here, both the reactions, forward and the reverse reaction, is producing the same number of gas molecules. So we will not be favoring either the forward or the reverse reaction of the first equilibrium. So therefore, the equilibrium position of the very first equilibrium that we have over here will not change when we change the pressure. However, if you take a look at the second equilibrium, we can see there's one gas molecule over here in the reactant side. In the product side, there are two gas molecules. So students, as we move towards the right hand side, or when we move in the forward direction, as the forward reaction happens, the number of gas molecules increased. On the left hand side of this equilibrium, there's only one molecule of gas molecules. On the right hand side of the equilibrium, there are two gas molecules. So when the forward reaction is happening, the number of gas molecules are increasing. If the reverse reaction is favored, the number of gas molecules are decreasing. So in a system like this, if you increase the pressure, according to the Le Chatelier's principle, the reaction that reduces the number of gas particles in the system will be favored. That means the reverse reaction will be favored. Reverse reaction will produce a lower number of gas particles. So therefore, students, if you increase the pressure of the system that is given here, the reverse reaction will be favored due to the reverse reaction producing a lower number of gas particles. So therefore, equilibrium position, when we increase the pressure, will shift to the left. The equilibrium position will shift to the left. Right. Let's move on to the next question. So in this third question, we are given another question about an equilibrium here. AB4 undergoes thermal decomposition in the following manner, and the AB4 decomposition equation is given here. AB4 undergoes decomposition to produce AB2 and RB2 gas. And we have been given two graphs at two different temperatures, 300 Kelvin temperature and 500 Kelvin temperature. So graphs y-axis is mole fraction, x-axis is time. So we have figure 1 and figure 2. So we have to note these things before we move on to the next part of the question. A sample of AB4 was heated to 300 Kelvin in an enclosed container. The total pressure of the system upon obtaining equilibrium was 30 newtons per meter square. The changes in the composition of the reaction mixture at 300 Kelvin are shown in figure 1. The changes of composition of the reaction mixture at 300 Kelvin are shown in figure 1. So we can see when we initially start, we only have our AB4, but gradually we can see AB4 mole fraction goes down. So initially the mole fraction of AB4 is 1, meaning only AB4 was there for the entire container. And then we can see gradually the AB4 mole fraction goes down and it settles at around 0.6. And B2 mole fraction increases. B2 mole fraction is increasing and it settles around 0.2. Now students, keep in mind, apart from B2, AB2 will also be produced. So we know we started only with AB4 because mole fraction of AB4 is 1, meaning for the entire container there was only AB4 initially, right? So and gradually AB4 reacted to eventually obtain equilibrium. At the point at which it obtained equilibrium, mole fraction of AB4 was 0.6. B2 mole fraction was 0.2. You know, B2 and AB2, they get produced in equal amounts. That means if the mole fraction of B2 is 0.2, mole fraction of AB2 is also 0.2, because we are only starting with AB4. So when AB4 breaks, equal amount of B2 and AB2 will be formed. Equal amount of each of these are getting formed. If the mole fraction of B2 is 0.2, that means mole fraction of AB2 is also 0.2. Right. Then we move on to the next part. When the same sample is heated to 500 Kelvin, the pressure in the equilibrium mixture formed was 50 newtons per meter square. The changes in the composition of the reaction mixture at 500 Kelvin are shown in figure 2. So we can see over here, at higher temperature, AB4 mole fraction has decreased all the way to 0.2. That means the forward reaction was happening more. AB4 was getting more converted more and more into the products. So that's why the reactant mole fraction has gone down while the product mole fractions have come up, right? So that means the forward reaction was favored at high temperatures. They are not asking that question yet, but you can make that observation here. The first question, what are the partial pressures of AB4 and AB2 in the equilibrium mixture that was observed at 300 Kelvin temperature? What is the equilibrium constant of the equilibrium system at 300 Kelvin temperature? Describe whether the decomposition of AB4 is exothermic or endothermic. If the pressure of the system is increased by reducing the volume of the system at constant pressure, explain what will happen to the equilibrium system. So these are the main questions that are given to us. So let's answer the first question. Right, so we went through this part. Let's answer the first question. What are the partial pressures of AB4, AB2 in the equilibrium mixture? Now, first of all, we will write down this equation. We have we have AB4 undergoing decomposition to produce AB2 and B2 gas. So initial mole fraction I'll use Xi for mole fraction was 1. We didn't have any of these. And at equilibrium, we write equilibrium mole fractions. Equilibrium mole fraction, I will indicate the mole fraction with Xi. So equilibrium mole fraction is going to be over here 0.6 and B2 was 0.2 according to our figure 1, because we are working with 300 degrees Celsius. So mole fraction of AB4 at equilibrium was 0.6. We can see we have obtained equilibrium here. And B2 mole fraction at equilibrium was 0.2. So if B2 mole fraction is 0.2, since AB2 and B2 will get produced in equal number of moles, whenever one AB4 is broken, one of this and one of this will be formed. So if the mole fraction of B2 is 0.2, without a doubt, mole fraction of AB2 will also be 0.2, because we started only with this. We didn't have any AB2 or B2 introduced in the beginning of this experiment. So therefore, the AB2 or B2 that is produced in the system will only be produced due to decomposition of AB4. So the number of moles of AB2 and B2 produced will be the same. Therefore, their mole fractions will be the same. Then we can also calculate their partial pressures. You know, the partial pressure of each individual gas is equal to the total pressure multiplied by their mole fraction. So in this case, the partial pressure of each gas is going to be equal to, now for this particular case AB4, will be equal to the total pressure. The total pressure was 30. The total pressure was 30 newtons per meter square. So 30 newtons per meter square multiplied by 0.6. 30 newtons per meter square multiplied by 0.6 is going to be 18 newtons per meter square. Now when it comes to partial pressure of, we'll write partial pressure of AB2 here. Partial pressure of AB2, or we can write directly in line with this. It will be convenient that way. Partial pressure of AB2 is equal to the total pressure, again 30 total pressure multiplied by the mole fraction of AB2. Mole fraction is 0.2. So when you do that, it will be equal to 6 Newton per meter square. Since we know that AB2 partial pressure should be equal to the partial pressure of B2, we can directly write B2 partial pressure, since it is equal to AB2 partial pressure, it's also going to be 6. It's also going to be 6 newtons per meter square. So these are the partial pressures of each of the gases. Now if you add all of these partial pressures of each of the gases, it should add up to 30. So let's see, 6 plus 6 is 12, 12 plus 18 is going to be 30. So we get to 30 newtons per meter square. So now we have found out all of the partial pressures. So the question asks us, what are the partial pressures of AB4, AB2 in the equilibrium mixture as well as B2. So we can write very clearly here, partial pressure of AB4, we calculated it using this equation, PT multiplied by the mole fraction of PT multiplied by the mole fraction. Without the multiplication, we'll indicate the multiplication like this, mole fraction of AB4. So I will do this one, substituting all the values to the equation so that is very clear to you. So this was 30 newtons per meter square multiplied by mole fraction. Mole fraction has no units, so therefore this is 0.6. So the answer will be 18 newtons per meter square. So this is the partial pressure of AB4, and the partial pressure of AB2 we calculated the same way. It happens to be 6 newtons per meter square, as well as the partial pressure of, we can say both partial pressure of AB2 as well as partial pressure of B2 are the same, since they get produced in the same amounts. So because of that, partial pressure of B2 is equal to partial pressure of AB2, which is equal to 6. So now students, we have found out the partial pressures of each of the gases present in this equilibrium at 300 Kelvin. What is the equilibrium constant value of the equilibrium system at 300 Kelvin? So we are asked to calculate the Kp value. Kp is equal to the product partial pressures raised to the power of the stoichiometric coefficient. So we have AB2, partial pressure of AB2 raised to the power 1, multiplied by partial pressure of B2 divided by partial pressure of AB4. Now we know each of the partial pressures. These happens to be 6 Newton per meter square, 6 Newton per meter square divided by 18 Newton per meter square. So we can see that these cancel off. These will also cancel off. We have us 18 divided by 6 is 3, and this cancel off to give you 2. So the answer would be 2 newtons per meter square. So this is going to be the Kp value at 300 Kelvin. Kp value at 300 Kelvin. Now we move on to the third part of this question. Describe whether the decomposition of AB4 is exothermic or endothermic. So we have been given this equation, we'll copy it down here. AB4 decomposes to produce AB2 and B2 gas. Now, what are the details we have? We know at 2 different temperatures, the mole fractions of each of these reactants and products. So we can see at 300 and 500 Kelvin, the mole fraction of AB4 at equilibrium is given. So at 300 Kelvin, the AB mole fraction is 0.6. But at 500 Kelvin, AB mole fraction is 0.2. A reduction. And when it comes to the products B2, at 300 Kelvin B2 mole fraction is 0.2, at 500 Kelvin B2 mole fraction is 0.4. So we can write them down. At 300 Kelvin, mole fraction of AB happens to be 0.6, and at 500 Kelvin mole fraction happens to be 0.2. At 300 Kelvin B2 mole fraction happens to be 0.2, meaning this was also 0.2. But at 500 Kelvin we can see mole fraction over here is 0.4. Each of them was 0.4. Actually B2 mole fraction was given as 0.4. That means we can find out the mole fraction of AB2 as well. That happens to be 0.4. Now at this point, students, you can observe that when we are moving from 300 Kelvin to 500 Kelvin, the AB, if I write it like this here, 300 Kelvin to 500 Kelvin, AB4 mole fraction has gone from 0.6 to 0.2. We can write when temperature is increased, the reactant concentrations. Mole fraction or reactant concentration has decreased when the temperature was increased. Apart from that, we can also observe that product concentration, let's say B2 mole fraction, was initially 0.2, but at 500 it has increased to 0.4. Right, we can say when the temperature was increased, the product concentrations increase. Product concentration, or if you say product mole fraction, has increased. Both are correct. So that means what? You can very clearly see when the temperature is increased, the product concentration increases while the reactant concentration goes down. That means the forward reaction was favored. You can write based on the above observations. It can be concluded that the forward reaction was favored when the temperature was increased. The temperature was increased. So that means what? Since we know according to the Le Chatelier's principle, when the temperature is increased, the endothermic reaction will be the one that is getting favored. So we can write the reaction that is favored when the temperature is increased according to Le Chatelier's principle is the endothermic reaction. Therefore, in the above equilibrium, the forward reaction is endothermic. So this is the conclusion, students. So we saw in the given set of data, we observed that when the temperature is increased, the reactant concentrations go down, product concentrations go up, meaning when the temperature is increased, the forward reaction is going to be favored. That is why we can see an increase in products and decrease in the reactant concentration. Based on the above observations, we can say that the forward reaction was favored here, but we know, according to Le Chatelier's principle, when the temperature is increased, the reaction that is favored is going to be the endothermic reaction. So what is the endothermic reaction here? The forward reaction. So in the above equilibrium, the forward reaction happens to be the endothermic reaction. So now, with that in mind, we can move on to the next question. So let's take a look at the next question. If the pressure of a system is increased, by reducing the volume of the system at constant temperature, explain what will happen to the equilibrium system. So we have this equilibrium system. We have AB4 gas. So this is only one gas molecule on the left hand side of the equation. And on the right hand side of the equation, we have AB2 gas as well as B2 gas. So overall, on the right hand side, there are two gas molecules. And over here, there's only one gas molecule. So a pressure of a system depends on, pressure of a gaseous system depends on the number of gas particles or gas molecules that are found within that system. As these gas molecules go and collide with the walls of the container, due to the collisions that take place, the force applied on the wall is going to be known as pressure. The more frequent the collisions, the higher the pressure. And there will be more frequent collisions if you increase the temperature of a system, or if we add more and more particles to the system, or if you decrease the volume of a system. So students, over here we have now decreased the volume of the system, and all of a sudden the pressure has now increased. So at that point, what will happen to this equilibrium? according to Le-Chatelier's principle. So if we have increased the pressure of the system by reducing the volume, and all of a sudden the pressure is now increased, the system, according to Le-Chatelier's principle, will adjust or will try to change in a way that reduces the pressure. Now we have externally increased the pressure, system will try to reduce the pressure. So in order for the system to reduce the pressure, system has to carry out the reaction that produces less number of gas particles, so that the number of gas particles within the system will decline or decrease. Therefore, the pressure will decrease. So we can write over here pressure of a gaseous system will depend on number of gas molecules within the system. So we can say the total pressure we'll say PT is directly proportional to the number of gas molecules, right? So that means when the pressure is increased, in a gaseous system, according to Le-Chatelier's principle, the reaction that produces a lower number of gas molecules will be favored. Therefore, in the above equilibrium, the reverse reaction or backward reaction will be favored. This will cause equilibrium position shift to the left. So students, this is something you need to keep in mind. When pressure of a gaseous system is increased, since the system is now trying to decrease the pressure, according to the Le-Chatelier's principle, system will favor the reaction that produces the lower number of gaseous particles. So in this particular equilibrium, the reverse reaction produces a lower number of gas molecules. So the reverse reaction is going to be the one that is getting favored. So as soon as you increase the pressure, the reverse reaction rate will be slightly higher compared to the forward reaction rate until a new equilibrium is obtained. So at that point, when a new equilibrium is obtained, the equilibrium position would have shifted to the left. Equilibrium position would have shifted to the left. So AB4 concentration would be higher. The equilibrium position will shift to the left due to increase in the pressure. So the answer over here covers all of the details that should be mentioned in your answer. Right, so when the reverse reaction is favored, the equilibrium position shifts to the left. Alright students, so at this point we can conclude our question discussion here. So by now students, we have discussed many questions that revolve around equilibrium. We saw how equilibrium would behave when we increase the pressure, when we decrease the pressure, when we increase the temperature or decrease the temperature, or when we increase or decrease the concentration of reactants or products of an equilibrium system. So at this point, you should be able to explain how an equilibrium position will change when we stress an equilibrium by changing the factors that I mentioned earlier: pressure, temperature, or the concentrations of reactants or products. So students, I hope by now you have a good, clear understanding of the theory parts associated with equilibrium and how to answer questions that are associated with equilibrium. So with this students, we can conclude this experiment number 34. I hope you have learned a lot of valuable information here, and I hope that you will join us in the next experiment as well. See you in the next experiment.